All right. Good evening, everyone. I hope my voice is loud and clear. Okay. Uh, okay. Quick check. Mr. Kalim, you shared this link. Which one is it? Let's quickly check. 65. Is it for the defined phase you're referring to? Because the link and the number,
Yes, defined phase, yeah.
we have a different link here. I'm not sure why is that so. If you open up this link is a different one. Look, if you compare it with this link and the link which you shared, they're different. So just if you try to open up, let me just open up this link. It is different. I'm not sure well how and why. Just try if you just open up this link here. It's copy paste. Copy this link, paste it here. It is a different link. So just check this out. It's a different link. What you got is K9. Okay, you're not copied. It's not the complete link you've copied. Like see, you have looked at the link as only till 6, this K9. Look at this definitely. It's K9, then it's GD8. Look at this one. You've got link till here. Only link till here. You just have to add the remaining portion. You just copy it incomplete link. I hope that will be clear. It's clear. So it's still K9 is your link. Your link doesn't have this last 3 digits here. Is it okay? That's the only thing which is missing in the link. So last 3 digits are not there. Work them out again and it should be fine. Okay, let's go and talk about this now. So we'll resume with today's session, and we'll be starting with a portion related to black belt, specifically with the non-normal data. Now, the journey is all about moving into the section where we talk about what if we had a non-normal data. So defined phase, there will be no changes whatsoever, because defined phase is all about getting the projects approved, making a team, giving them responsibilities, communication plan, preparing a SIPOC. That's a high level thing which will not change, whether it's a green belt project, a black belt project, you're dealing with the normal data or non-normal data. That part is not going to change whatsoever. Changes will happen when you get into the measure phase, and specifically when we talk about sigma level calculation. Now, when we deal with the non-normal data, and practically it's a pain. Why? Because dealing with the normal data will any given day be a easier thing to do. And like just what tell you like basic details about when we talk about a normal data has a definite shape. You know what is normal data. Pretty much you have a proper structure. You know what is the percentage of data here or here. You can do all that predictions and calculation. It's very much predictable. You know, it's something with which you can study everything practically at a sigma level. It's easy to handle normal data. Having said that, the statistical tests that we perform in analyze phase are also more accurate. If your data is like when you talk about average based, when you do mean based tests are more accurate than the median based tests. So, well, is it in my hand whether data will be normal or non-normal? The answer is no. Your data may be normal, your data may be non-normal. So there is, but any given day, when you talk about normal data, it's much more easier to handle, much more controllable when you kind of look into the analysis will be more accurate. So we always love to have a normal data, where we don't have a control, by the way. So we can get a normal data, we can get non-normal, but we'll always want to get back to normal. Can I convert the original non-normal data, which turns out to be non-normal? We test the data, we found the data is non-normal. There are certain mathematical ways you can convert the original non-normal to normal. Well, it is something I would love to see. Why? Because this is any given day desirable data. For every possible analysis, it's a desirable data. Everything we have done, like ANOVA testing, 2-sample-T, it is more accurate any given day as compared to the median based testing we'll be doing if it's non-normal. So we will first try our luck. Like having said that, the way you convert a non-normal to a normal data, it is not guaranteed that every normal data, non-normal, can be converted. But again, there's very high chance that a non-normal data can be converted to normal. So first of all, we'll try our luck. That let's see if we get lucky and our data, which is non-normal, can be converted to normal. So we apply certain functions called transformation functions. And this is what we'll be covering up first. But before I even discuss this, let me kind of make it clear. This topic is for master black belt, not from black belt, but for master black belt. It is not what you would be tested on. The reason why I get always, and in every batch, I cover this topic because it's a matter of going through another like 15, 20 minutes of discussion, how this data transformation is done. But it'll give you so much of power to handle the projects. Why? Because if I happen to get a non-normal data and if I can convert it to normal, my project will be like very smooth and will be easy to handle it. So whatever we're going to cover from perspective of this data transformation, it is not going to be tested in your exam. This is just to make sure you have one more extra tool with you, because if you are able to convert, well, there's nothing better than that. So please keep this in mind. This portion that we're going to cover first, it's not going to be part of your exam. Now, when we say transformation, what is transformation? Let's understand in a logical way what is transformation. If I write a data, like there's a data called 1 upon 10. If I write this data as 10 upon 100, do I see a different value? The answer is yes. This value looks different. But is it different? No, they both are same. It may look different, but it's same. Or I write this as 100 upon 1000. Well, this is also same. It looks different. Or I might go and continue with this 1000 upon 10,000. Well, meaning doesn't change. It's all the same. So what I have done is I've transformed this original data into other forms. But even though I have transformed it, meaning doesn't change. It's still the same value. So data transformation, mathematical ways of transformation will convert your original data, which is could be non-normal, into another form, mathematical form, and that mathematical form of the new data may turn out, not guaranteed, may turn out to be normal. So although you might see a different value, it's not your original data. Looking like the value might look different, but mathematically it will be 100% the same value. So this is what we will be doing in transformation part. Now, when we say transformation, there are two types of transformation we use. One is called a Box-Cox transformation. Another method is called Johnson transformation. Now, Box-Cox is less powerful. When I say less powerful, I'm talking about 85% of time, this method will be able to convert a non-normal to normal. This is capable, but like not 100% obviously, but 85% of the time it will be able to convert. And that's what I'm saying, it's less powerful. But then there is a method called Johnson transformation. It's definitely more powerful than that. It's more than 90% of time it will be able to convert non-normal to normal. So yes, there will be scenarios where you try to convert the non-normal data to normal with the Box-Cox transformation and it failed. It's possible. But when you try with Johnson, it will get converted. So there are different ways of doing it. Now, big question why can't we then directly try Johnson? Well, we can do that, but we prefer always to do a Box-Cox first. Why? When you convert data with the Box-Cox method, the sigma level you'll get all the complete normal part, like CP, CPK, PP, PPK. You get the complete picture, like the normal data does. But if you are going to use a Johnson method, you'll only get a PPK based sigma. Well, I will still be able to get my sigma level because PPK multiplied by 3 will give you long-term sigma, and long-term plus 1.5 will give me current sigma level, which is, I will still be able to find it. But it's, well, when you get the CP, CPK, well, it's always desirable to get that because see, CPK, we all know what is difference between CPK and PPK. It's done for a short duration. And yes, when you talk about PPK is overall, but you don't have a choice when you don't get CPK, then bottom line, PPK will be a good estimate of your process sigma level. So I can still do that job here with the PPK, but I will try to get like a normal version of CP, CPK, PP, PPK. If it does not work, then I will be going with this version. And in certain cases, neither this will work nor this will work. Then you have to like tell yourself, well, we are dealing with a pure non-normal data. This one is a hard nut to crack. Well, we are dealing with something which cannot be converted. This data, even after trying Box-Cox, even after trying Johnson, we are not able to convert. Then bottom line, you got to deal with a pure non-normal data. There is no way you are able to convert this data. Well, congratulations. Welcome to the world of non-normal now. So, but I will try my luck always. If I have a non-normal data, I'll try this. If it fails, then only I'll go with a pure non-normal method. because then all the testing will be median based. Everything going forward will be median based. But if I'm able to convert it, well, then I'll go back to my average testing, which is the median, ANOVA, the two sample T. So I'll try to, first of all, see what if my data gets converted. So we'll start with this first one. Let's see how Boxcox works, how Johnson works. So I'm going to pick up this data here. First of all, let's try to see whether this data is a normal data or not. And then we'll try to see whether this data can be converted. How do we know? So we go to stat. First of all, let's check the normality. Stats, basic stats, and we check the graphical summary of this data. So looking at this data set, I will check this p-value for this. Looking at p-value, what do you conclude? A null or alternate hypothesis, 0.027. Null or alternate?
Alternate.
It's alternate. Yes, p-value is less than 0.05. That confirms that the data is non-normal. Well, when my alternate comes in, we always say data is non-normal. Now, on this data, all the concepts of your normal distribution will fail because this data is non-normal. So primarily, now what do I do with this data? I will first of all try my luck. I have to find sigma level for this process. And in this case, the customer has given me some targets, like targets are given by the customer, like LSL is 6.5, USL is 7 kilograms. Well, this is some weight. So this data is a non-normal data, and I have LSL, USL, but I know everything that we know now, which is about normal data, that will not apply. This data is non-normal, and everything that we have studied is about normal data. So I will try to see if I'm getting lucky or not. So how do I know if this data can be converted with the transformation methods or not? So we'll go to first this option called Stat Quality Tools, and there is this option called Individual Distribution Identification. When I click on this, it is going to ask me for the data. I'll select the data set. Subgroup size, single column, just one which is single column. It is going to try all the distribution in the Minitab and transformation. Why? Because when we talk about non-normal data is a virus, because this is a non-normal data. This could be a non-normal data. This could be a non-normal data. Well, it's a virus. You can see a different variation. The normal data has a definite shape, and like we are dealing with a potential virus scenario here, which is a non-normal one. So there are certain non-normal shapes which have been identified, and it's pretty much in the Minitab here. And we will also try transformation. So let's see. We simply click OK after this. What it does, it tries to fit your data into different kind of data sets, which are different non-normal shapes, which are in the, and it's going to try out this p-values. So there, it's going to try your data in every type of distribution Minitab has in the backend, like 14 different distributions are there. And now what we need is simply go to this page, because summary of all those images is right here. Goodness of fit test. So we'll copy this result. Let's copy this one. Let's try to understand whether this data can be converted. So right now we're only checking whether this data can be converted with the transformation methods or not. So I'm just going to check this out, whether this data is convertible or not convertible. So how do we check that? Let's see. So I'm just going to make some space here. Let's keep some more space so that we can read this clearly. Let's check this out. I need the p-values, and this is not required. Okay. Now, first of all, I need to know whether this data that I'm using here, is this data convertible or not? Can you convert this data with your transformation method, the Boxcox method, the Johnson method? Is it convertible or not? So we have all this result, the goodness of it as results. And I would like to see the transformation result. Now, Boxcox transformation, the p-value. Do you think it's a null hypothesis? It is going to it's telling you that if Boxcox is applied, this will be the p-value. Would you say it's null or alternate? Now, yes, absolutely. So now, based on this p-value, since p-value is greater than 0.05, we'll go with null, and null says data is normal. So this tells me that yes, if I use Boxcox is capable. So if I use Boxcox method, it will be able to convert data and normalize the data. And for that, now that data, the p-value will be 0.098, where the current original data, you have a p-value of 0.027. This data, if you apply the normality, the transformation method of Boxcox, the same data will get normalized, and that data will have a p-value of 0.098. Now, hypothetically, assuming that Box-Cox did not work, hypothetically, then we would also check the Johnson. Johnson is also there. Looking at the Johnson, do you see it's normalized or not? Looking at p-value, null or non. This is also. So here also I can say, well, since p-value is more than 0.05, we'll go with normal. So I know Johnson is capable. And honestly, if Box-Cox is capable, Johnson will always be capable. Johnson is more powerful. So it can happen that Box-Cox is not capable and Johnson will be capable. But Johnson is any which is more robust, more powerful any given day as compared to the Box-Cox version. So in this case, I know both my data set will get converted with the Box-Cox method, with the Johnson method. It will work absolutely fine. So there's no problem. Let's now see how that transformation works and how do we get the new data and all. But here it was just checking. So this was all about checking. That's all we have done here. We have not transformed data, but I would like to show you how to transform and all. But this was just to check. This is just to check if transformation will work or not. That's it. First of all, we wanted to see whether it's going to work or not. Whether should we waste time or invest time here. So I wanted to check this first. So I know both will work. Now, how do you transform? Let's see. Let's go back to our mini tab and let's create heading here. Just creating heading here called Box-Cox. So I want to transform this old data, the non-normal data, into a transform data and have the Box-Cox data here, the new data here. And also let's create a heading for Johnson. So I would like to have the Johnson data stored here. So let's see how to do Box-Cox. I go to Stat. There's the option of control charts. And here in the first option is Box-Cox transformation. I click on the Box-Cox transformation. Now my data is not like a one column. It's a row wise, 1, 2, 3, 4. It's actually one row of a column. I select this. What is the data set? It says, let's select the data set. That's the data we want to transform. In the options tab, now here it tells you something. It tells you, and I at least honestly, I can explain how Box-Cox works manually. I can explain. For all non-normal analysis, you need a software like Minitab or Sigma Excel, some sort of software. Non-normal data, you can't do manual calculations here. But at least I can explain the manual one for the Box-Cox. But Johnson, honestly, you will not even ask me how that happened because you need a software to do that job. But what it's telling you, we will transform this data using some lambda values. These are, and what are lambda? I can explain in a moment. So there's some lambda value has to be used to transform the data. And lambda value is ranging between what? -5 to +5. That's a range of lambda value. So it is asking you, Minitab, do you know the right lambda value? If you know the right lambda value, which will be used for transformation, then you can click this button and say, put it this like this. If you know the right lambda value, well, then you can do one thing. You can simply go ahead and click this button and just mention the right lambda value, which will be used for conversion. Well, do I know it? No, I don't know it. So I want Minitab you to do this job. I have no idea what's the right lambda value. You find the right lambda value. That's none of my business. You find the right lambda value. And after you apply the lambda value, store the transform data in this heading called Box-Cox. So I have created a heading of Box-Cox. After you apply the right lambda value, store the data in the Box-Cox heading. Let's click OK. I'll explain what is lambda value here. And there is a data created. What it tells me this, there's a lambda value of 5 has been applied. Lambda value 5 has been applied to convert this original data into a new data. Now I am not sure whether this new data is transformed or not. Like in normal, either Box-Cox has been applied, but with the new data, with the lambda 5, what we're talking about, the lambda 5 has been applied on this old data, and with which you have a new data created. Is this data normal or not? I don't know. I have to check it. So I have to check whether this Box-Cox data is a normal data or not. Whether the 5th lambda value, did it work? Yes or no? Let's see. We will perform the graphical summary for this new data, Box-Cox. The data which has been transformed with 5th lambda value. I click OK. Look at this. Is it not the same p-value we saw there? 0.098 in our testing. 0.098. If I use the Box-Cox transformation, it will give me a 0.098 p-value. This is the one, 0.098. This is the transform data. The transform data, it tells me, yes, this is what the data will be. So when I tested it, it gave me that if you're going to use box cogs, this is going to be the transform value of this one. So I know it is a transform data. But let's see what is this lambda. What is this lambda here? Let's kind of take a quick example to understand what is lambda. When I say lambda, there's a value, some value, let's call it x. X to the power 0 is lambda 0. X to the power 1, lambda 1. X to the power 2, lambda 2. X to the power 3, power 4, power 5. This is fifth lambda value. So every value we have done power 5, power 5, power 5. That's fifth lambda value. What is minus side? 1 upon x. 1 upon square root of x. 1 upon cube root of x. 1 upon fourth root of x. 1 upon fifth root of x. So this all data sets are created. Like in Minitab is doing all that, like it's trying to convert data and create a new set of data with minus 5 lambda, with minus 4 lambda, with minus 3 lambda, minus 1 lambda, 1 lambda, like minus 1 lambda, 0 lambda, like technically 1 lambda, 2 lambda, and all that. It's doing all that. And it's trying to create different data sets in the backend. We have asked Minitab to find the right lambda value. So it's trying this transformation, getting a data. Trying this transformation, getting. So it's trying all different transformation which can be done, and it's trying to find the best lambda value, which is giving you almost close to normal data. But you still have to check by the one which it found that out of all the lambda value, this power 5 lambda value, whatever data gets created, this is very close to normal. But you still have to check whether it's normal or not. So it has directly picked up fifth lambda value because we had asked Minitab to check. I don't know what's the right conversion value. So you find the right one, and Minitab, when you checked it here, it tells you that, yeah, fifth lambda value is the best one because it has tried all possible transformations. It found that fifth one is the best one, and it has given you data, but you have to still check whether this data is transformed or not. And if you want to see this is fifth lambda value we're talking about. We just look at the data, this data and this data, it's fifth power 5. So if I do this, let me delete this one. If you do this value, power 5, that's fifth lambda value. That's the data. Power 5 for all the data is done power 5. And if you look at this value and this value, it's 100%. 12,593.2, 12,593.2, 16,663.0, 16,663.0, 14,722.5. We're talking about the same thing. So every data has been, like every value has been taken as power 5 of that original value. So power 5 original value of when you do it, the data gets normalized. Now this is how I have been able to find it, the data which is a normal data by applying the fifth lambda value. And Minitab has found my right lambda value there. So manually, if you want to do it, we got to do it manually for every lambda value and then see which one is giving me the best normal data. So we'll try all data like with minus 5, with minus 4, with minus 3. And it'll like, then we'll find, say, do normality for everyone. And then finally we will find, okay, right lambda value, which is giving me more close, the best normal data. That will be a manual process. But again, this is sort of still doable. Manually can do that. But again, Johnson, honestly, I said, you will not even ask me how did it happen because it's going to, you need a software. But let's see how to do this. Johnson transformation. I go to start. There is quality tools and there is an option of Johnson transformation. I click on this Johnson transformation. It's asking me for the data, the old data with the data set, the non-normal one. It says store the transform data. We already created heading Johnson. The beauty about Johnson is that you don't have to check whether data is normal or not. Why? Because Johnson only gives you data if it's normal. If the data is not getting converted, it will give you fail message, but will not give you data. In case of Boxbox will still give you data, and you have to check whether it's normal or non-normal. And you can get non-normal also. So you have to check. But in case of Johnson, you don't need it. Data will only come if it's normal. Otherwise, it will not come. Let's see. Data is normal. I don't have to see anything. This value, the moment I saw data, it means that it is a transformed data. Data is getting normalized. Let's see. Old p-value, original data, 0.027. Transformed data, new p-value, 0.246. And this is the mathematical function it has applied. It has created based on data. It has gone and created this mathematical equation to convert the data into a normal one. So wherever you see this value x, it's a data, the individual value of data, x. And then rest is the mathematical equation, whatever this log function which is there. Bottom line, wherever it's x value, that's a data value, which will be used And then when you complete this equation, you will get a value created here. That value will be the Johnson transform value. So it has gone and transformed this entire data into a transform data. And we'll look at this is much, if I look at normality wise, it's much better than the Johnson box one. If I look at the normality here, this is, if I look at the p value we getting for these, let's quickly see this one. Look at this 0.246 as compared to 0.098. This has higher normality function. If I look at the p value, so it's more on the normality side, higher as compared to box one. So it's any which way is more powerful. But look at this, you can see negative values also, which is absolutely fine, doesn't matter. See, you're looking at a different version of the same data. Is this data same? Answer is 100% yes. Same data has been transformed with a mathematical equation, and the entire data has been created into a normal data. So a mathematical equation with which every data has been converted with the same formula. So it's a new transformed value, and this is normal. So before I start calculating the sigma level of this process with this data, I want you to see that these are real world practices. People use this day in, day out, because I hate to use a data which is non-normal. Well, I would love to see, well, can I get lucky? And I would love to see if it's possible. The real world practice, this is a telecom industry case study, I guess in UAE or Saudi Arabia. Well, this is what they had. They had a problem with non-normal stuff. Their data was non-normal. Look at this. So their box Cox data did not work. They had to do the Johnson transformation. So for them, box Cox did not work. So they had to apply the same Johnson transformation method, and their data got normalized with Johnson. So, well, they were happy. And yes, then they found the sigma level, which we will be doing now. So how the Johnson transformation sigma level works, this is how we'll be seeing how to do this in a moment. So by the way, when they improved the process, the new data was also non-normal. So they had to again apply Johnson to convert that to find a new sigma level, because even the new data was non-normal. So finally, then they did a before and after analysis of the process. Well, what was the old sigma level, new sigma level after they had transformed? So old data was non-normal, the new data was non-normal, and then they had to do this transformation function. So I'll share this file also. Have a look at that. When you're looking at this file, pretty much you can see the old sigma level before sigma improvement, sigma level after improvement, sigma level before improvement, sigma level after improvement. So it is the change we're looking at. So all in all, these are real world practices. I'll share this case study, so that you are clear about the conceptually these are practically applied in real world scenario. And the big question is, how do I calculate sigma level? So the method is pretty straightforward. Well, I need to know what is my target here. Target is 6.57, like specification limit, whatever the customer is given. So it's 6.5 and 7 is the LSL and USL. Let's go back to our data set. The original, this is non-normal data. I'll go to stat. I'll go to quality tools. Here I will select normal. Well, my data is non-normal, right? There is an option of non-normal. We'll also use this, but first, let's click on this one. Why? My original data is non-normal, but still I will select normal. Why? Because I have already checked that my data can be transformed with the transformation method, and it will become normal. And that's why I'm going to check normal. Click on normal. Now it's going to ask me for the data set. I'll give the data set. Subgroup size, single column. Yes. LSL, 6.5 kilograms. USL, 7 kilograms. Whatever the LSL, USL we have got, we add it here. And by default, look at this. The first button says transform. Every time you have a button, and this will be, it says by default, this is no transformation. Well, why would you transform in general? Why would you transform? If the data is already normal, why would you need to transform? So by default, when you're doing this sigma level calculation for a normal data, there's no transformation applied. But since our case is a special case, I know that our data is a non-normal one and it needs transformation. And we already know that box Cox will be able to convert. Johnson will be able to convert. We already know that. So by default, if the data is normal, this is always a no transformation. But if the data is a non-normal one, and you know that you already checked, the box Cox will be able to convert it. Let's select the box Cox. It'll do the right lambda value, same thing. Click OK, and OK, done with it. Let's see the sigma level for the process. Same fifth lambda value it has applied. Look at this, what it tells you, the old process data. Let's see what it has to say. the old LSL, the old USL, it has also transformed your targets also, because in the same proportion, your data is changing, your targets have to be changed. So it tells you the 6.5 was old LSL, USL. It has transformed your target of LSL, USL also, according to the same proportion. Your old sample mean, the new sample mean, the old like a standard deviation overall within for the same like normal data. You get CPK, CPK, you get it multiplied by 3, you get your long-term sigma. And after getting your long-term sigma, you add 1.5, you get your current sigma level. That's a standard drill. You know your defect percentage in a million, like defect in a million on lower side, upper side, the total defect percentage. Like normal data, we did it early. In a normal case, this is exactly the same. The only difference is we are using a transformed data. We are not using the old data for calculating sigma level, because old data was non-normal one. So we have transformed it, which is normal, and then we are using this calculation. So all this analysis is happening based on the transformation data, which is normalized. And we have not just transformed the data, we've transformed the targets also in the same proportion. So this is a pretty good way of finding the sigma level if the data is a non-normal one. It is like a normal data only now. Now, having said that, if my data was like I was not able to transfer, in case Box-Cox did not work, in case, then I would have chosen Johnson. Like I would have tried, there is an option of Johnson also. So instead of transforming Box-Cox, I could have chosen Johnson also. And I would have chosen the Johnson transformation method for finding sigma level. Look at this, same drill here. This is PPK based. Well, Johnson has only one problem here. Johnson will only give you PPK, which is also fine. There's no harm in using a PPK. PPK multiplied by 3 will give you long-term sigma, and long-term plus 1.5 will give me current sigma level. So, well, this has gone ahead and transformed your old data, old LSL USL into the new LSL USL based on the same transformation function here. And it has gone and transformed the data. You've got your defect rate in a million and all that job, same like normal data. But now, the only difference here is that you can't get CPK is not possible when you're using the Johnson transformation. Johnson transformation only gives you PPK based calculation. So that's how you find the sigma level. You first need to check it out whether my data is getting transformed or not. That's what we did first. We just wanted to check whether it's capable, whether we will be able to use transformation. So we found it already that Box-Cox will be able to do, Johnson will be able to do, and all you have to do is go and apply the right transformation option and then calculate the sigma level. It's like normal sigma level calculation process. Well, you go and select your data, LSL, USL, and then select the right transformation. It'll do its job. That's it, what you need to do. Transformations are real world practices, which is widely used. Having said that, does it guarantee that it will happen for every case? The answer is no. And I'll rather use the data to show you that it does not work every time. It does not. So, well, then what will we do? Let's see. Let's check this one. We will pick up a non-normal data here, which is like we did here. Let's go and check out whether this data, is it getting converted? So we'll try to see the transformation function works or not. Let's pick up this data. I'm going to pick up this data and calculate first of all, I have to check whether this new data we're going to use here, is this getting transformed or not? So I will try this quality tools, individual distribution identification. We'll click on this. I will select this data called turnaround time, TAT, and I would like to select basically I want to see whether it is convertible or not. Let me click OK. You want to see this on the right, on the top, it tells you failed to select Johnson. Johnson failed. Trust if I see this message, I know Box-Cox has also failed. If Johnson has failed, I would always believe Box-Cox has gone. Bottom line, this is more powerful any given day. If the powerful test is failing, the weaker test will automatically fail. But at least let's see that. So Johnson will not give you results, simple as that. I said Johnson only gives you result when it is getting normalized. But let's drop down. Let's see the box, this goodness of it we need. Copy this data. Let's see. So I will not see the Johnson. Johnson comes in the end, but Johnson has failed, so it doesn't give you anything. Straight away fail message. And Box-Cox, look at this. Looking at this, is it visible that we null or alternate? It is alternate. Yes, box was failed to transform to normal. Box Cox will not work, and by default, we already seen that Johnson has failed. So pretty much, let's make a note of that. Johnson failed to transform as well. So it is now I have reached to a stage where nothing is going to work, and there will be situation like that. Let's see the data also. Like, well, let's try this out. Like, let's try this with the way we did it for. Let's create a heading called Box Cox. Let's create a heading for Johnson, and let's see, are we actually getting data or not? Box Cox, Johnson. Let's try to convert this. Let's go and try the Box Cox, which is go to control charts, Box Cox transformation, select the data, ask Minitab to write pick up the right lambda value, which I don't know, select the Box Cox heading and store the data under Box Cox. See, problem with Box Cox is it will give you data any which ways. It has gone and given you data. It has applied a lambda value of 0.5. Well, I'm not sure. Let's see whether this data is transformed or not. So the new data of Box Cox, let's see if it's transformed. Looking at p-value, is it the same p-value we saw there? Less than 0.005. Yeah, so we have pretty much, I know Box Cox did not work. Let's try the Johnson also. We go to start, and Johnson will not give you data. Don't worry, like here, Johnson will not trouble us. Why? Because it will not give you data, anything. Let's say, click on Johnson transformation. I want to transform this original data and store this data under this heading called Johnson. That's it. Click OK. Doesn't give you data. Not at all. Nothing. If Johnson is not able to convert, it doesn't give you anything. Simple as that. It'll give you this message, fail to transform. That's it. We are done. So it means that every data cannot be converted. They'll say like more than 90% of time, Johnson will be converting it, but not 100%. So some data will be like this, where neither Box Cox will work, nor Johnson will work. So again, whatever we completed this portion right now, this is not going to be part of your examination. Because this again, like to reiterate, this topic is from Master Black Belt syllabus. But again, as a black belt, when you're doing a project and you come across a non-normal data, this is going to be a good like a source to pull that data back to normal. And so that's why we always end up getting it covered, so that while you're doing the project, you will save yourself from doing a median-based testing, which is going to be hassle, unnecessary. But you don't have a choice at times, because you might get into a situation like this where nothing will work. Then you have to say, welcome to the world of non-normal data. Well, because then you got to be handling a non-normal. The median will be used going forward. So right in this data, let's find out what do we do now. If your data turns out to be pure non-normal, not getting converted, how will I find sigma level for the process? Let's see that. Let's see. If I go and find out stuff, I'll sort of explain with this data set how to find sigma level, and you guide me with the second one. So you got two data sets, two non-normal one where we were able to convert. So now I'm assuming that we're not able to convert. Now, how do I find sigma level for this process? And when I explain this one, you help me with the second data set. In the first data set, I'm assuming that Box Cox did not work, Johnson did not work, and now how do I find sigma level? The thumb rule is that first find highest p-value. If you get one highest p-value, that's your distribution. If you get a tie, then check the corresponding lowest AD value. AD is Anderson-Darling value. Let's see. I'll explain this one. You can help me with the other ones. So I look for the highest p-value, and now I am assuming that the transformation has not worked. So I'll look at this p-value, this p-value. We'll look at this is big. If you compare with all of them, this is big. This is also big. And these are all small. Yeah. I hope you all agree with this. If I compare others with this, these two are big p-values, and there's a tie also. So we have two p-values. Now there's a tie. If you would have got only one, that would have been my distribution. Now I've got two. So what will I do? I will look for corresponding AD value, Anderson-Darling value. We'll look for the lowest one, which is what we'll be using as a distribution. So here, the distribution is going to be smallest extreme value, which is the lowest AD value. So since smallest extreme value has lowest AD, we will go with it. Well, but good to know, just good to know, more than 90% of non-normal data will ideally fit in viable. This is the most common distribution, viable. Most common non-normal distribution is viable. And look at this. Honestly, this even the AD value is very nominal in decimal places change. So even if I use viable for sigma level calculation or smallest extreme, I will get same p-value. And let's see that. Let's say we'll get the same sigma level for this, whether the UI use a viable, but technically I should go with smallest extreme value because that has, as per the rule, that's the right one. But honestly, because the difference between AD value is marginal difference, it doesn't matter even if I use viable. And ideally, it'll be, or most of the cases, it'll be viable only. And that's why Minitab always keeps viable as the by default distribution. Now, I'm going with the first data. Let me find the sigma level. So this is the first one where we had a LSL of 6.5, USL of 7, and where we had tried transformation also. But let's see how do we deal with this non-normal data. Assuming the Box-Cox has not worked on this data, Johnson has not worked on this data, so that there's no point of transformation, nothing will be done here. I'll have to go with the non-normal data. It's a pure non-normal data which cannot be transformed. I click on this, select the data, look at this, by default viable is there. By default, it's because it's the most common non-normal will be viable. But right now we'll go with the smallest extreme value because that was our distribution. If I use the LSL as 6.5, USL as 7 kilogram, let's find the distribution here, the sigma level. Look at this 0.17 ppk, 0.17. That's the shape of a viable distribution. It's the smallest extreme value distribution here. 0.17 for this data is the ppk. You only get ppk with non-normal data. You don't get cpk with normal data, like non-normal one. So this is what you get with the smallest extreme. If I change this distribution shape to viable, because there was a marginal difference, let's see, you will still get the same. Yeah, 0.17 here also. So whether I use a viable distribution, I get 0.17. Whether I use a smallest extreme value distribution as 0.17. And honestly, if I use for the same data, when we tried Johnson, let's see what's the sigma level. This was the ppk was 0.19 with Box-Cox transformation. ppk, small difference. Instead of 0.17, you're getting 0.19. With the Johnson, you get 0.1. Look at this Johnson transformation. When it transforms, ppk is 0.17. Let's try to compare all of them. When I tried on the same data with the Box-Cox, I got 0.19. With the Johnson, I got 0.17. When I find the actual distribution, I found 0.17. If I tried with viable, I got 0.17. So typically, if you see the transformation, and they are very, very like Box-Cox, smallest extreme, and viable all had 0.17 as ppk, except Box-Cox, which will give you 0.19. It is a little bit more. There will be small bit of difference, and that much of is okay, and that's not a big deal. It is always acceptable. So that's how we go with the data distribution now. Now we will now go ahead with this data which we were not able to convert to a normal one, and how do we handle this one in this case? Can you please tell me which the data is right in front of you? Can you tell me what should be the distribution I should be choosing here for finding the sigma level? On this one, we actually both failed. Neither Box-Cox worked nor Johnson worked. So we are going to find the actual non-normal shape now. Yes. Which one? We got multiple now. And make sure you're absolutely correct there. Like so, 4 items. You're right about that. So these are 2 here. And these are 2 here. Absolutely, Amit. You were right about that. Look at this. My choice will be viable. Smallest value here. Smallest one. So I'll go with viable here. Viable has the smallest AD value. We always go with one. most of the time it will be viable. All the time, like say, I will say most of the time, you will always see viable. Let's try with viable with this data. Or this is turnaround time and say the USL given by the client is say 700 seconds or 750 seconds of turnaround time maximum. Let's find the sigma level for this process. Non-normal data. Pick up the turnaround time. Viable is the distribution. We know that. No LSL. It has got 700, say 50 as whatever the customer target. In this example, we're taking like 750 second is the upper limit. That's it. Done. See the viable shape here. It is not the perfect fit. Perfect fit, there's only one distribution called normal data. Rest is all best fit distribution. Every other distribution is called best fit because perfect is always a normal one. See, this distribution is the one which is covering maximum data. Look at this. This data is going out of the distribution. This is not predicted in the data. This is not getting predicted in this data. So it is one distribution within which we are covering maximum data. Other distribution, we leave more data out of this one. It has maximum coverage of all the data. Well, bottom line, it's the best fit one. And yes, in this case, my PPK is 0.13. So if I look at this, USL line is here. So there's a lot of data is outside. And this is what my total defects in a million will look like. PPK, I got 0.39. I'll do multiplied by 1.5 will give me long-term sigma. For my bad, PPK multiplied by 3, long-term sigma, and plus 1.5 will give me current sigma level. So I'll get my job done. So it doesn't matter what industry is it, what kind of data you're looking at. Try to see if you can get lucky by converting the data to normal. Try the box, great, works, amazing. Doesn't work, try the Johnson. If it works, amazing. If it doesn't work, then welcome here and then start finding the distribution. Find the right distribution, apply the non-normal function, and you will get your sigma level done. It's how you do this testing here. So yes, it's quite possible in the examination, you could get a table like this one. Because that data, the transformation is not what will be tested. Transformation is not what will be tested in the examination, because that's a part of the master blackboard. But yes, non-parametric method, the method is what you have to understand here. And that you might just be given a spread, like some sort of values like this, and they might ask you to find the sigma right distribution for finding the sigma level. Yes, so you should know how to find, like pick up the last one, highest. If you get one p-value, which is highest, that is my distribution. Is non-normal data set more prone to lower sigma level? Not necessarily, see, Anvesha, but more prone to error. The correctness, the accuracy is less. Accuracy is less because you're not covering all the data. Your sigma level can be high, but again, it's the error, the not too confident about the numbers you report, but it's still very much in control, and it's the only option. So you don't have a choice. We'll always, that's why we want to go back to normal. So everything is in control. But here, by God's grace, things are just working out here in case of non-normal one. So that's how we deal with a pure and non-normal data. So we go back here and like we look at what we are covering from a technically the non-normal part. Here, we talked about right now the data transformation methods. We talked about non-normal method. Now, we'll be picking up data, which is if I perform the fishbone diagram, and we are in analyze phase, we're doing a fishbone diagram, and you find like your data is non-normal. So all the testing you did, like a 2-sample T, the ANOVA testing, and all those F test and Bartlett method and everything, randomness is all will go in vain, nothing. It's all waste. Now, why? Because data is non-normal. So in this kind of data, which we just looked at, this kind of data is a pure non-normal data. So nothing will work here. So for this data, if this is your business problem, which is turnaround time, that's your business problem. Now, for this kind of data, you will have to perform all median-based tests. Why? Because you are not able to convert this data. This data was not convertible with normal data. So now you have to actually perform median-based test on this data to find the root cause, which is why you're having a business problem here. So all average-based tests will be replaced with a median-based test. Now, this side of the testing is very easy because it is like honestly very straightforward. Mean-based testing has more conditions, more ifs and buts, and that's why it's more complicated, but more accurate also. When there are less complicated, like it's less complicated because there are like straightforward like very, very straightforward, no conditions in case of non-normal data. Let's see how do we find the testing here, which test to be done in what kind of scenario. We'll just go through that first. It's very like a fairly simple to interpret the test in case of non-normal data. Not too much. There's actually no hassle in the non-normal testing. In this case, you have a business problem which you're trying to solve here. And in our case, let's say this is the turnaround time, TAT, turnaround time. That's the data we are looking at. This is non-normal. And yes, we were not able to convert this data to normal with Box, Cox, or Johnson. So pretty much we know for sure every testing will be done, will be a median-based testing. So my business problem is crystal clear to me. Like my normal data, I also have some of the X's are numeric, like age of the person, salary of the person, whatever you have, all numeric data sets which have a numeric input factor. Let's go back and see. This is my business problem. Let's highlight this separately. That's the business problem. And some of the X's are numeric, which is age of the person. That's numeric. Tenure of the person. That's numeric. So these two are here numeric data sets. Let's see if we have some more. Let's kind of highlight them. These are the numeric data sets we have. And yeah, we have one more. So this is the numeric. So if you want to find a relationship between age of a person and the turnaround time, the test will be same. What is the name of the test if you recall? How do you find a statistical relation between two numeric data sets? How will I find if the age has any relation with your turnaround time? Which test will be done here? It doesn't change. That's a graphical test. Johan, I will agree with that. That's a graphical test. You're right about that. Statistical test. Not the graphical one, but the answer from graphical one is correct. Scatter. What will be the test I should be using here? That's a normal, that statistical test where you get a p-value and all, not AD. Finding relationship between two numeric data sets. We did that for normal data. No. Relationship between two numeric data sets, not two groups. Normal data, we have
scatter diagram. Scatter diagram
is the graphical analysis. The answer is correct, but only graphical. But I'm talking about statistical test. What is the name of the test? Absolutely, Anvisha. Correlation or regression. You want to find a relationship. The statistical test is correlation or a regression test. The graphical analysis, scatter diagram. Yes, graphically you can show the scatter diagram, but the test is correlation test or regression test. And this is what you'll be doing here also. That doesn't change. So if I want to do a relationship study, find out whether age has a relation with turnaround time, whether tenure of the person has a relation with turnaround time, whether the typing speed of a person has a relation with turnaround time, I will be performing the same test like in normal data, which is a correlation test or regression test. So that doesn't change. That will be absolutely the same. Now comes in the remaining factors, which are categorical data sets, which we had. We either have two groups, like same way. Either we have two groups or more than two groups, like we had in the normal data. Here we may be comparing the medians because data is non-normal. So you may be comparing median of male and female. You may be comparing for median for morning or night shift median. You're comparing the medians of two groups. That's it. Instead of average, the language has changed to median. And nothing else has changed. The way you interpret it, same. The language has changed from mean to median. That's it. Let's say wherever we have two groups, like let's see here. And the name of the test is Mann-Whitney test. Mann-Whitney test. Let's see where all we will do Mann-Whitney test here. This is more than two groups. This is two groups. So then I will be using Mann-Whitney test here. Trainers, multiple. Shift, multiple. But there are actually three here. Gender, two, which is Mann-Whitney. Location, two only. Mann-Whitney again. This is correlation or regression. So I will use correlation or regression. This is also correlation or regression here also. Knowing the test is more important any given day. That's two groups, Mann-Whitney. Marital status, married or single, again two groups, Mann-Whitney. Mode of communication, two languages probably. And we have got Mann-Whitney again. And the last one is correlation or regression. That's all you have here. To compare two groups, I will use a Mann-Whitney test to compare the median of first group and the median of second group. And then you have more than two groups. Where you have more than two groups, you will be performing Driscoll-Wallace or Moore's median test. the test of Kruskal-Wallis or Modes-Median will be applied here. Let's see where all there are more than two groups here. So I'll do a Kruskal-Wallis or Modes-Median. Kruskal-Wallis or Modes-Median here, Kruskal-Wallis Modes-Median. That's it. It's simple. It's not like your normal data, this condition, that condition. Straightforward, just go and perform the test, you're done. Non-normal data testing is straightforward because you're just comparing medians, not too much to analyze there. Not too much of average has a lot of conditions. You look at the variation, you look at whether data is has equal variances or not, whether randomness is there or not, what knows what not. Here it's straightforward. You're just looking at the median of data. That's it. So we'll first do the Mann-Whitney test. This is the only test in the entire testing here which will make you do some extra effort in performing the test, not how to analyze, but performing the test. I'm going to make a conscious mistake right now. Say two groups we'll be picking. I would like to do a Mann-Whitney test to compare whether median turnaround time of level 1 is equal to median turnaround time of level 2. Null says equal. Alternate says no, medians are different for both the levels. Well, I have to perform Mann-Whitney. I'm going to make a conscious mistake right now so that we can remember this. Like easier to remember that, oh, well, this is where I will have a problem. All this non-normal data test is here, a non-parametric. Parametric word is meant for normal, non-parametric word is meant for non-normal. So all non-normal test is here. Mann-Whitney. Now I click on this Mann-Whitney and now I get into trouble. Why? What trouble? Normally we get two boxes. One box is for Y with output, another box is for input, X factors. Here I don't get it that way. It's saying that you want to compare the median of two groups. Give me first group and give me second group. It doesn't need data in this format. Well, my data is, all the data is in one single column. Like, look at this. Level 1, level 2 are in one single column. So it needs data separately. It says, give me, in one column, give me all the level 1 turnaround time. Give me a second column with all the turnaround time for level 2. So it needs data in two separate columns. Level 1 time in one column, level 2 time in another column. It says, give me data that way. I will not be able to understand this way. So bottom line, what is saying? Do a filter of level 1. This is all the time of level 1. This is all the time for level 1. And then do a filter of level 2. And then get the data for level 2. All the data for level 2. So it needs data in two separate columns. Not like this. So we will use Minitab to get the job done. So I can't do this test right now. It says, give me first column, give me second column. I will go to data option here. In data, there's an option of unstack the column, break the column, separate the columns here. What do you want to unstack? I want to unstack the turnaround time. The output is turnaround time. I want to break it down. By what? I want to break it down by process complexity. Based on level 1, level 2, split the data. Okay. This is level 1 time. This is level 2 time. I have split the data. Now this data is fit for my Mann-Whitney testing. For Mann-Whitney testing, it is absolutely okay to go and now do the test. Let's perform this stat non-parametric Mann-Whitney. I will pick up first group level 1, second group level 2. And I would like to perform whether this test is it's done or not. Let's see. When I perform this statistical test, I will get this p-value. Null says that variances, medians are equal. Alternate says no, the medians are unequal here. Anyone would like to pitch in here, whether null or alternate? It is null or alternate, 0.518. It is null, absolutely. This p-value is more than 0.05. So we say we do not have enough evidence for us to prove that there is a difference in level 1, level 2. So do not come back with an excuse that I'm doing a level 1 work or like they are doing level 2. This is not a valid excuse. So stop using this as an excuse. You're almost doing the same job. There's no difference in your medians at a population level. So this is not a root cause. Let's pick up one more here. Let's pick up another factor, which is, let's pick up gender, male, female, Mann-Whitney, two groups. Let's compare them. I have to again break the data. Data, unstack the column, but based on gender now. Male data, separate column, female data, separate. By gender, break it down. So female column separate, male column separate. This is female data. Let's make it female. Let's call male, M for male. And now let's go and perform non-parametric test of Mann-Whitney. Female column, male column. I compare this with equal. Let's see. Would you call it a null or would you call it alternate? Still not. So, well, we always said it's an illogical argument to derive differences between male and female. What a gender has to do with it? So practically the null was right, null is right, and null will always be right. So whenever you talk about comparing two groups, medians, you will be using a Mann-Whitney test for comparing two groups medians. When it comes to more than two groups, you have got two choices. We'll do both of them, but honestly, the second one is a better one. I would always use the modes median because it gives me more clarity about why. But Kruskal-Wallis will do the job. But let's do both of them, and then you can decide which one you want to use. So I will compare, say, system operators. There are multiple. I will go with system operators, with a Kruskal-Wallis is here. Modes median just below that. So let's click on Kruskal-Wallis. Response is the business problem. The outcome, which is turnaround time, is the business problem we're trying to solve here. And the input factor is the system operator, which is what we want to compare. Different system operator-wise turnaround time of the operators here. All right, click OK, and it will go and check. Let's see what it has to say. Null says all medians are equal. Alternate says no. Alternate always has a problem. Looking at p-value, what do you conclude? A null or alternate here? It's null. Absolutely, yes. Now, let's similarly perform the test on, like we could figure out this is null based on, you can look at the median. Look at this 391, 315, 325, 369, 290. Do you think there is a big difference also? Like you can see that there are differences, right? But still, I'm not able to figure out why null because I'm not getting enough information here. It just tells me, look at it. I would generally believe that this 391 is quite big and 292, there's a big gap in the median. Why still null? Let's see. If I perform the same test with the other one, which is we will go now with modes median. Let's try this one and we'll give you clarity why. Same test, response is the business problem, system operator is the X input factor. Let's see what it tells me, that population medians are equal. Alternate says no. Looking at p-value, it's null. Can you tell me why now why it is null? Because look at this overlapping. So if I look at this overlapping between this, it will be almost, so 297 till 501. And this is 201. It starts and goes till 431. There is an overlap at 95%. Now I have clarity why it is null. Why? Because all overlapping. If you try to do this sketching, you will see everything is overlapping. You do this, it starts from 297, goes till 501. Another one starts in between, like 297. So say 267 will start somewhere here. We'll go till 399. Another one starts at 262 somewhere here, and goes to 374 somewhere here. Another one, it says 251, say somewhere here, and goes till 511 somewhere outside this. And then you have 210, and it goes till 431 somewhere here. I guess it 431 somewhere here. So everything is overlapping with everything. And I can figure this out when I have 95% confidence interval for median. It tells me the population medians will range anywhere between this. So I'm able to see that everything is overlapping. There's no big deal. Why it's not null? Well, it is null. Definitely why? Because there's everything is overlapping with everything. So it's a clarity will come into picture when you use the modes median. And that is unfortunately not there in the other one. Let's see, there are other factors here. We got trainers. Let's try multiple groups of medians comparison. Start and modes median for trainers. Null or alternate? It is, yes, it is absolutely yes. And we know why. Why? We know exactly why. Do you see the groups which are not overlapping? Yeah, there is a big group. Well, yeah, absolutely, yes. Let's see this guy. If I look at time is lesser the better. Turnaround time is lesser the better. If I look at this guy, Atul, this guy ends at 230. Worst case 230. These guys don't even start at 230. Look at this. His worst case is 230. These guys start way after. There's no overlap happening. So absolutely why we are getting an alternative. Pretty much. No wonder why. Let's see. Similarly, we have another variable which we can test. Shift, we have got 3. So we can compare. Null or alternate? It is alternate. Perfect. Yes. Less than 0.05. And you know why? Which groups are not overlapping? Absolutely. Night is ending. So we'll look at this one. Yes, evening and night. So this is ending at 363. This is starting at 371. There's no overlap. One shift ends and your journey starts, which is big. Oh, big difference. Populations have nothing in common. They're not overlapping. So yes, there is a reason for us to believe now night shift is bad. Why? Because this is their worst case. Worst case is not even your best case, which is bad. And definitely this is the root cause. So all you have to do is understand, see, knowing which test is more important any given day, specifically with the non-normal data. There's not too much of hassle to deal with the non-normal data because it's straightforward. All you got to do is keep the testing in mind, which test has to be performed in what scenario, and we'll be fine. So if I were to just quickly go back and summarize this for you, just not this one, like just in general, what if I have to summarize the test here, just for not only this normal data, non-normal data, this is how it typically looks like. You are comparing means, or rather, let's keep it here. Comparing means, comparing variances or standard deviation, comparing medians. That's what you're looking at. For two groups, we have some test, and for 2+ groups, we have another set of test. For two groups means I do 2 sample T. For two groups variance, we do 2 variance or test for equal variance, or which will give you result from F test. The real test is F test for comparing 2 variances. For 2 medians, I do Mann-Whitney, which we just studied today. 2+ groups, for comparing 2+ groups, my average for more than 2 groups is one-way ANOVA test. For variance testing is like test for equal variance, and we will get result from Bartlett method. And for more than 2 groups, we have got Kruskal-Wallis or Moore's median. Quick summary table. Now, apart from this, what else we talked about? Test for normality, which is Anderson-Darling test. Test for randomness or stability. We perform run chart. We get 4 patterns: clustering, oscillation, mixture, and trend. 4 p-values, 4. And like if any p-value is less than 0.05, it becomes non-random. For finding relation between 2 numeric data sets, X is a number, Y is a number, you do a correlation or a regression test. That's all we have talked about. Is it okay? Just try to summarize some, and we'll add some more here. It's not just over, but this is typically what we perform. Is it okay and clear? Basically, it covers your green belt portion, it covers your black belt section also.
Okay, we find correlation when we have to find the relationship between the 2 numbers, and regression when we have to find the root cause. Am I right?
Both the cases. See, again, when we talk about correlation also, it will give you, both will give you, let's kind of add in there. It will summarize, it will be easier. So when you do, it's about 2 relations. Whether you talk about, you use correlation or regression. So in correlation you perform, you get a p-value, which will tell you whether there is a relation or not, an R value, which will give you, well, basically what type of relation you have, and the nature of relationship, like or strength of relationship. So whether it's a low relation, medium relation, high relation, or what is the positive relation or negative relation. Regression will give you the p-value, which is what I wanted. Like, so either this R square, which will tell you the strength of relationship, how strong is the variable, It gives you the linear equation with which we can predict the output if you know the input value. That's so regression is meant ideally to understand what will be the output value if my input value is so and so. Is it clear?
Yes.
Perfect. And so we'll add some more. It's not over yet. Now we'll be covering up one more element here. Now, one strange element which is going to come in now is we will be dealing with data where there will be no numbers at all. So we're going to talk about something called a chi-square testing. Very important, very informative test because it's applied on real world scenario. It's very much mathematically possible. You can do it manually also on an Excel sheet. So we'll do it on Excel also. We'll do it on Minitab. Very much widely used and very common test asked during the interviews because it's generally practiced by people in the people do that in HR world. They do a lot of it. It's like in everywhere it can be used. So the test we will be talking about is when you talk about categorical data. Well, categorical data pretty much means that there is no numbers in there. Let's see what I'm talking about. I want to find out relationship between, like if I want to find a relationship between process complexity and shift. I want to find a relationship between gender and trainer. I want to find a relationship with gender, like shift and the shift operator. When I want to deal with two categorical, no numbers. Two categories have been discussed here. So that's where the relationship we are talking about. So two numbers we understand. If you want to find relationship between two numbers, you do talk about both X is number, Y is number, both numbers do a correlation regression. But you talk about relationship in two categorical data, no numbers involved at all. Then you talk about, so let me extend this one here. So which we'll be doing now. For finding relationship between two categorical data. X is category, Y is also category. Both are categorical, no numbers. We will be performing a test called chi-square cross tabulation, or it's also called test for association. This is for both data. Like for example, I'm sure we all must have heard this theory. Like I'm not sure how many of us really believe this is correct or not. Boys like blue and girls like pink. Well, do you think this theory is right, wrong, or just a cooked up story, something just like that? There's nothing called this, but probably somebody just made a story like this. Boys like blue and girls like pink. Well, because what I'm talking about is two variables here. One is the column is gender, which is like I'm saying boys, girls. Well, I'm asking people like different boy, like there's a boy or there's a girl, male, female. I can keep doing it. So like I asked a boy about the favorite, and I'm giving the choice of color as two. You have to choose either pink or blue. So this boy says, I like pink. Well, it's quite possible. The girls may say, oh no, I like blue. Now I ask another boy well, would you like blue or pink? So this guy says, I like blue. This girl says, no, I like pink. And so on. So if I keep asking different boys, girls, like, and I ask them this question and they keep telling me, so can I conduct an analysis? And this is all about a theory has come to my mind. Somebody tells something just by believing it. No, why can't you test it? Any idea that crops to you in your mind, you can test. Like this was just an idea. Somebody just made a claim. Well, boys like blue and girls like pink. Can I test it? Why not? Get some data collected and then perform the test. It's a very, very common thing to rather believe something just like that, perform a statistical test and be sure. So any theory that comes to any claim, weird ideas, people will challenge. Well, let's perform chi-square and we'll be able to figure out whether it is actually there or it's just a vague thought somebody just came up with. So we will be doing chi-square is very much practiced in real world. People do that. And when we talk about chi-square was used to declare the COVID as pandemic. So like pandemic thing got the tagging was given to this COVID as first of all endemic, then epidemic, and then pandemic based on the chi-square testing. Everywhere when you see the globally, whenever people do, you go to any kind of sports event, the referee when a referee takes the coin and flips the coin with a head or tail, you know, is that coin any coin? No. That coin is a chi-square tested coin. A regulator and an auditor has picked up that coin and tested this on chi-square method and that's when the coin has a validity that this coin can be used for testing head or tail or for deciding who's going to win based on the coin, but it has an expiry date. And again, the auditor will come and audit the coin once again. So it is chi-square tested. Globally, wherever you go in the world, every casino is regulated by the government because, well, there in some countries, obviously, the casino and gambling is an illegal activity. In some countries, it's allowed. So wherever it is allowed, government obviously doesn't want, like, well, what government wants, I can't comment on that, but government wants, like, definitely wants that it does not give you as a casino owner any undue advantage to do a fraud with somebody. Somebody believes that going for casino gambling and gives you the kick and happiness, well, that's their personal choice, which is we don't want to get in there, but it does not give you undue and like advantage to take like liberty and like probably do a fraud with them. So there has to be a fair deal. So, and when you talk about gambling, well, how can we forget Las Vegas? Las Vegas is all about casino. The entire city runs on casino. This entire industry of casino is regulated. So a regulator, like which is auditor, will come from the government side, will go and watch, do this chi-square testing in a casino. The machine which is like Lucky 7777 or the dice they use, the cards they use, and all that, everything is chi-square tested. It has an expiration certificate, and then again the auditors come every year to get this audit done. So everything boils down to chi-square testing. So again, given the time, I guess we may not be able to talk about get on this one right now, but let's do one thing. Let's take the break. When we come back, we will start with the chi-square testing because we will do it on Minitab. We'll do it manually also in Excel. I guess we're back from the break. Thank you. Let's get started then. So before going on the break, we briefly started discussion about this categorical data. The said when you are dealing with the categorical data, which test will be required to find a statistical relationship between two categorical data sets, and the test name is chi-square cross-tabulation or test for association. But again, before we go and actually go and perform this test, we need to understand the foundation, how this chi-square testing works, and that we have to. So before we learn this chi-square cross-tabulation test, we have to understand the base of this test, which is called chi-square goodness of fit test, or it's also called one variable test. So this is one single column, not X and Y. So just you have one single column data, and you would like to see whether and based on which we will be able to understand how chi-square works. So it's not about X and Y. When you perform this goodness of fit or one variable test, we will be able to understand how chi-square function works. So here the crux is, when you talk about chi-square, it always works with the concept of observed versus expected frequency. We'll see what is that. So when you understand this concept of observed versus expected frequency by performing this chi-square goodness of fit test, then we'll move on to this chi-square cross-tabulation. Let's see how does this chi-square works. Let's see what is that we have here. Okay, perfect. All right, so quick check with everyone here. When I flip a coin, what is the chance I'll get a head or a tail for that matter? Head or a tail? What's the chance of probability of getting head or a tail when you flip? 50%? Yes, absolutely perfect. 1/2, 50%. When I have a dice and I roll the dice, what is the probability that I'll get a number 6 on the dice?
1/6.
Absolutely. 1/6. Every number has 1/6 chance. 1 can come 1/6, 2 can come 1/6. Every number has equal probability. I have a pack of cards, the playing cards, and what is the probability that I'll get an ace? Ace in my hand. There's a pack of cards. I pick up one card out of that pack. What is the probability that I'll get an ace in my hand? Jahan, no, that's not correct. Yes. One card, I want to pick it up, and from my hand, from the pack of cards, what is the probability that the card in my hand is an ace?
4/52.
Absolutely, yes. The total of 4 cards, 4 aces in a pack of cards, the total of 4 aces, and the total of 52 cards. So if I do cancellation, I'll get 1/13. So we call 430, 452 or 113 is the same thing. So there's a 1/13th chance that if I have a pack of cards, I pick up the card in my hand is going to be a ace. There's 1/13th chance. So these are expected frequencies, which we expect whenever we will perform some action. This is how it is expected to happen. That's the expected frequency. Yeah, 7.69%. Now, with the same logic, say if I go ahead and take a coin and I would like to do a head or a tail, like do a, so ideally what I expect if I do it 20 times. So I am expecting 10 times I'll get head, 10 times I'll get a tail. Will I exactly get 10 times head? If I flip it 20 times, will I get 10 times head, 10 times this always? No, well, that's right. If I get 11 and 9, will I say this coin is a trick the coin, something wrong with the coin? 11, 9, difference has happened in expected versus what actually you saw. Do you think it's the difference is large enough for you to say, no, well, there is something wrong? No, logically not. Yeah. How about this? Now, has it become an alarming fact now? There is something wrong with the coin? Still not. How about this? Is it now high enough for you to say there is a difference and this difference is large enough? There's something wrong with the coin. Some trick work has happened. Let's say about this. How about this? Or how about this? Or for that matter, how about this? When do you say the difference between the expected count, which is generally expected, and what you see in reality? If the difference has become large enough for you to say, now, this is not natural. Something wrong has been done. So the difference, because this is what we expect naturally something to happen. But when I see something happening differently, when do I say it's become large enough? Look, I was talking about COVID vaccines and all. Same thing happened. Like not COVID vaccine, but COVID to be declared as a pandemic or whatever. So generally in a hospital, you'd expect that if the number of patients coming to hospital, for every kind of treatment will be almost the same. If somewhat plus minus would be there, but they're almost same. People coming from heart-related problem, bones-related, like digestion-related, like overall respiration-related problems. So they'll be almost similar kind of footfall will be there. When this COVID cases started increasing, that count sort of like it's expected that every like journal, more like there'll be almost some bit of plus minus, but almost the same. But when the COVID cases increased, and the gap became bigger, and that's when the testing was done to figure out when it has reached to a point where now you say it's not natural. Something wrong has happened here. Now, this is something which needs to be understood differently because this is not how ideally it will work. So there is a difference. So the chi-square works simply based on the difference of observed versus expected count. So like I was talking about, this is the same concept used for coin, like in case of a match, referee uses the coin, or for that matter, in a casino. Let's kind of try to do this one. We have a casino where we as an auditor, we go there and we sort of audit. And I pick up a dice and I throw the dice. I'm expected to get any number between 1 to 6, any number. I got a 4. And I keep doing this. This is my data. As an auditor, I keep doing this multiple times to say I have got thrown this dice these many times. This is what my data got collected. So the massive data, this is where I've thrown the dice multiple times. And this is, let's see how many total we have. The total I have thrown this dice is 1,303 because one is heading. So 1,303 times I have thrown this dice. And this total data I have got is 1,303. 300, that's 1303. 1303 is the total count. So expected is that every number in this data should have been 1 by 6. So every number should have come 217.16 times. Will it be same? No, obviously not. We know every number, 1 cannot come exactly the same, 2 cannot come. So but expectation is that it will be same. But there can be small differences here and there, but there will be difference for sure. But a big question is that large enough? How do you know it's a large enough? And so Null says, no. The differences can be there, but it's not large enough. It's a fair dice. Nothing wrong with this dice. Alternate says, no, there is definitely something wrong. This is a tricked dice. There is something wrong with it. Well, one of the number probably comes more than expected, or one number comes way too less than expected. So there is something wrong with this. Let's see. So this data gets collected. You copy paste this data and perform this test on for chi-square. Goodness of it, or you call it as one variable test. stat, all these chi-square is in tables. Tables, chi-square goodness of it, one variable. Why? Because one single column. These are all categorical. They are actually not numbers, they're categorical data. They are all like categorical. There are 6 different possibilities I can see here. They're all categorical data. When I throw a coin, like the dice, I can get 6 different out possible, like a count, like things I can see here. So every number has equal probability 1/6. I click OK. Let's see. We saw that this whatever color, this is orange. In my side, it's orange. Not sure how, like I'm too bad with colors, but again, this is the same number, 217.616 times, 217.16 times. That's every number has equal probability of coming. Every number has equal probability. That's the expected count, which we calculate. 1,303 divided by 6 was the same number, equal. But what was actually seen in the data? 211 times, it came slightly less than expected. Against 217.16 times, you got 211 times, less than expected. This is even lesser than 208 times. This is quite higher than expected. 235 times instead of 217. Slightly higher than expected, quite less than expected, 200 times. And this is like higher than expected, about 228 times. Do I see a difference in observed and expect specifically with this one, or for that matter, this one? Well, is there a significant difference? Well, looks like there is a difference, but is that large enough for you to say this is a dice, is strict dice? Well, null says no, it's enough. Like this is small differences can be there. Well, it's not a large enough difference. Alternate says no, this is a significant difference, and we should we should look at this dice as a faulty dice. Something wrong has been done. So looking at p-value, null or alternate. It is null, absolutely. So there is no statistical evidence available for you to claim that this dice is a trick dice or something wrong has been done with the dice. It's a fair dice. You can use it for gambling purposes. Well, please enjoy. But that's how people get their audits done. Having said that, while we understand this is the way we deal with it, chi-square testing, while we apply the same logic when you're trying to find the statistical relation between 2 variables, well, we will be using a chi-square cross-establishment, like I was talking about, 2 variables, a relationship, and now there are no numbers here. This is also category. This is also category. You want to find a relationship. Well, and that the claim was like boys like blue and girls like pink. You can collect some data, conduct a survey, ask boys or girls, and like ask the question that you got 2 colors to choose from. Which one is favorite? And you will be able to verify, is this sort of saying correct or not? Is it like just somebody's mind, like somebody sort of cooked up a story, or is there actually a relationship like that? We can always test and verify the general theories which are circulated in the market. We can test them. So let's see how we go about doing it. Like kind of go ahead here. Say I will so I wanted to know there is primarily I have 3 different soft drinks to compare here. One is a Coke. One is my brand that I want to launch in the market. I want to see, is my brand ready enough, and probably want to do some target audience identification, that which one will be my target audience, male or female, gender-wise. And I have another competitor, Pepsi. So I know when I will launch my soft drink, I will have a tough competition from them. And keeping in mind, I'm trying to find out my target audience, whether it's going to be male or female. And I would like to compare this. But I know for sure, people are Coke lovers, will pick up Coke always. People are Pepsi lovers, will pick up Pepsi. My brand is no one knows. So it will be sort of unnecessarily getting impacted. So it's not a level playing field for everyone. We must give equal probabilities and equal chances to all of them. And let's see who's the better one. So what we do is we conduct a survey. And this survey is done we call it as a blind testing. So what we do here, I pick up 3 disposable glasses in some shopping mall or wherever I get a lot of people. And first disposable glass has Coke. I know that it's Coke. I don't want to show them what this is Coke bottle. So a disposable glass has Coke. Second disposable glass has my brand. Third disposable glass is Pepsi. And I know that. For them, it's just like a 3 different glasses. And we can we stopped some lady just passing by and tell her And we are trying to conduct a survey and we want you to taste all these three glasses and finally let us know which one did you like. She tastes one by one, all of them. Fair equal chance given to all of them with no labels, nothing like no branding done. And after tasting all of them, she said, oh, I like the first glass. I know she is talking about Coke. So my data got collected. I stopped another gentleman. I asked the same question and he also tasted all of them. And he said, well, I like the first one. I know this guy's also talking about Coke. So I keep on doing this testing, and this is how my data is getting collected. And please keep this in mind, while we're conducting this survey, we could have collected other data sets also, because I want to find my target audience, right? I could have done age group also as a criteria, right? That could be another factor. I may want to know which age group will be my best target audience, whether people like with less than 20 years, people between 20 and 30 years, or 30 to 40 years, or I can create more groups here. And I can try to see which is my target audience. And there can be more categorical data which can be tested. While you're conducting survey, you can collect a lot of information. So you can test my target audience, which is the right target audience, and practically that can be used here. So right now, we're just kind of going ahead with two variables. And I would like to check it. So first we'll do it on Minitab and then we'll do it on Excel also. So let's go and perform this test on Minitab. Well, by the way, null says there is no relationship. So that means gender has no biasness towards any soft drink. They're all the same. So they equally love, whether it's a male or female, they equally love all the three brands. There's no specific biasness towards a particular soft drink. And alternate says no. There is definitely a biasness within the group here. Let's see. So we will be performing this test tables. It says test for association. We pick this up. Ideally, it honestly doesn't matter because both are categories. You can put anything anywhere, row and column, but being technically right, always put X in the row and column in the Y. In the column, put Y. So let's put the row as gender, column as soft drink. So because we want to understand the association of gender towards the soft drink. So my area of interest is soft drink. Ideally, I honestly, result will not change if you flip it also, but it is the right way to always put Y axis, put the output, X axis, you put the input. And that's it, we're done. Look at the p-value and tell me whether you call it null or alternate. Null says no biasness, no preferences. Alternate says no, there is. Null or alternate? It is alternate. Yes, absolutely perfect. Yes, you're right about that. There is an association. Let's see how. Female, it was expected that females, 103.53 females will say it was expected that I love Coke. On the contrary, 116 females said I like Coke. More than expected. Looks like females are Coke lovers. It was expected that 42.33 females will say my brand is good, whereas 37 only said my brand is good. That means they did not like my brand. 58.14 females were expected that they will say, I like Pepsi. Less of them like Pepsi. It looks like they don't love Pepsi or my brand. They love more of Coke. On the contrary, here, when you look at male, it was expected that 99.47 male would like my brand, the Coke, but less of them like Coke, 87 only. So this is that they don't like Coke, looks like that. But yes, look at this. Males loved more of my brand. Males loved more of Pepsi. So it looks like they have more affinity towards Pepsi or my brand, whereas females have more affinity towards Coke. And is that difference large enough? Well, it says yes. There is enough statistical evidence to say that since my p-value is less than 0.05, we go with alternate and say, yeah, there is a biasness here. There is a biasness to be able to conclude that there is an association between the possible factors and the output we're looking at. There is a biasness. The difference is large enough. So, well, if I would be targeting, I would target male audience for my brand, well, because that's my target audience. There is a significant love or affection seen there as compared to female. So I will focus all my energy, and initially I would like to prepare my advertisement campaign targeting the male audience and not the female audience. That's because I know there is a biasness here that will help me get the existence in the market, like stabilize in the market. That's my target audience. I would like to optimize my revenue by focusing on the targeted audience here. Same test. Let's leave it as it is. Let's try to do this in Excel. So that's your chi-square testing like data raw data. I'm going to do a pivot table here, just a pivot table. So I'll go to insert, do a pivot table, click OK, and we will make a summarization basically. I will draw the gender in the rows column, draw this sorting in the columns, and then pick up one of them, doesn't matter what. This is actual results, not the expected, but the actual result. In this survey, 116 females said actually that I like Coke. 37 females said that I like my brand, and 51 said I like Pepsi. So total 204 females actually participated. And this was the breakup of their decision, whatever they made. And this is the breakup for male audience. So I've got this summary of the survey. This is only the actual count of people who said I like this, I like that, but not the expected count. So I can copy this entire thing. I'll copy this and I can paste it here, which I've done already. So this is the same data, actual count. This is how I've copied from there, just done some color coding. That's it. Same data. This is actual, but not the expected. And where do I expect it? I do copy this portion once again, and I paste it here. This is the same thing, pasted here. But what I do is I only delete the middle part. This one I have deleted. If you look at this, this is exactly the same. This. It's exactly the same thing right here. This is exactly the same thing. All I have done is deleted the middle part, which is about the actual count of people who said, I like this, I like that. That count I have, because that's the actual count of people. I need to find the expected count, which is here. Rest, everything is same. I only deleted the middle part, which says how many females said, I like this, how many males said, I like. How do I get this one? The formula is right here. It says row total multiplied by the column total, and you divide by the total observation. So I'll do row total is 204. This is the row total. Multiplied by column total. This is the formula, row total, column total. Multiplied by column total, 203. So I put 203. Close the bracket, divided by total of 400. Now row total is 196. We do 196. Column total is still 203. 203. Divided by grand total of 400. Let's do again the row total. Row total 204. Multiplied by column total 83. Divided by 400. Row total 196. Column total 83. Divided by 400 as overall total. Let's do row total 204. Column total 114. Overall total 400. Last one. Row total 196. Column total 114. Divided by grand total 400. So this is the expected count. Look at this. 103.53, 42.3, 358.14. We are looking at the same thing. 99, 47, 40, 67, 55, 86. 99, 47, 40, 67, 55, 86. Minitab is doing the exactly same maths in the back end to give you this expected count. Now you got your observed count, actual count, you got your expected count. Can you get the p-value? The answer is yes. This is the test formula. You look at this, chi-square dot test, the last option. Chi-square dot test. It says actual range. Okay, actual range. How many people said I like this, I like that? This is the one, actual range. Comma. It says expected range, which is this one, which we calculated right now. That's it. Observed, actual, and the observed, expected one. This p-value and the likelihood ratio is the same, 0.044, 0.044. You're looking at the same thing. So this is absolutely possible, doable in Excel while we are able to do it in Minitab, but very, very popular testing mechanism, which is followed in all the, in every possible forum whenever we talk about the statistical testing, wherever it is done. So generally people use this for, in HR world, people do this, like, so if I want to know about attrition in the company is too high, people are leaving the company, people can do chi-square testing. People can do chi-square testing to see what is it a shift, which is why somebody would leave, yes or no. There can be a lot of factors. Bottom line, if somebody comes with a claim, some sort of theory, some sort of claim, all I need to validate is collect some data, do some survey, and perform the test, and it will give you clarity whether there is a significant difference for you to make that claim or not. You will be able to find that out. The chi-square testing is something which is very commonly asked during the job interview. So, well, it should be clear that how chi-square testing works. The core crux is it works on the difference between observed and expected frequency. That's the answer to all the question. Observed and expected frequency. So when you want to do it for single variable, you do a chi-square goodness of fit test results, which is also called one variable test, or you can do a chi-square cross tabulation for finding statistical relationship between two different variables. But that's on the chi-square testing. Now, quick check on this one if it's okay and clear. If it's okay and clear with everyone. Just wanted to be sure about this one. Anyone has any questions? Because we have one more topic here, which is related to analyze phase, which we'll be covering up. And that's, I guess, this. So we talked about the non-normal median-based comparison. We talked about categorical Y, categorical X, both are, which is chi-square testing. And the last topic we have in analyze phase from a non-normal data perspective, like technically from a black belt part of it, is about types of error. Small bit of theory, which is what we have here. And looks like we will be we'll be ahead of time here. Like, so again, we'll not pick up these topics are like, so we have last topic, which is types of error. Given the time, pretty much this one and this is technically to be covered on the 11th day, and this is supposed to be on the 12th day. So we are ahead of the time practically. We have this one topic, and we still have some more time. So, well, if it's what we can do is let's complete this one. Now we can complete the practice test we have here. And yes, if there's any other topic that you want to kind of discuss, we can discuss it with a given time. So let's kind of quickly talk through this last topic here in analyze part. It's about types of error. Well, types of error will be there. And yes, we will make mistakes also. While we are performing this statistical test, can we make mistakes? The answer is 100% yes. You can make an error while you're making the statistical test. So what could be the reason? Well, we will talk about the types of tests, but reasons are common. Whether you talk about like there are two types of error. We call it as type 1 error. You also call it as alpha error. You also call it as innocent punished situation, or you also call it as false positive situation. Doesn't matter which you talk about, but they're all the same thing. And please keep this in mind. You have to memorize all of them. Why? Because during job interview, people may ask this a simple question. Give me an example of false positive. Or they will tell you a scenario and say, okay, is it false positive or not? Or is it, what kind of error have we committed when in a court, an innocent person is punished by the court? What error has the court made? Bottom line, please keep this in mind. This is all the same. There are different names for the same thing. Similarly, there's another error called type 2 error, which is also called beta error, guilty released situation, or a false negative. They're all the same. So you have to remember all of these because they're all synonyms, like differently called, but all mean the same. Whether you talk about type 1 error, you talk about type 2 error, bottom line, every error will happen because of a common reason. Reason is common for both of them, which is this. Insufficient sample size. So before, people were not too aware of the sample size calculation. They were just doing data collection just like that and just collecting some samples without knowing how much is the right sample size. So if your sample size was higher than required, then it's okay. But when the sample size happens to be less than required, then you're prone to make either type 1 or type 2 error, which is where the problem will happen. So A, insufficient sample size can become a reason of this error. Or B, if you've not done a proper sampling methodology. If you've not used a good sampling methodology, like we right now have the simple random sampling, the stratified random sampling, the systematic sampling, the rational subgrouping, but these are the most evolved methods of collecting data. The old methods are there, so many old methods, cluster sampling, quota sampling, judgment sampling, snowball sampling. There are too many bad methods. This science has evolved over a period of time, and now you talk about the best known methods, but there is a history, a long history of different kind of sampling methods people have tried, and they found that it's not working. Like when they collected data, they did use that data for analysis, and they got wrong information because the data collection process was faulty, and they made either type 1 or type 2 error because of that data collected. Or it could be genuinely a human error, manual human mistake. We're not robots. We will make mistakes for sure. So human error, a genuine human error can cause this error. So what is this type 1, type 2? Let's talk about one. And if you understand one, other will be by default clear. What is a type 1 error? In a nutshell, if you prove a null, a genuine null, as an alternate, you're making a type 1. Is it a mistake? If there is something called null and you call it alternate, is that a mistake? The answer is yes. this mistake will be called as a type 1 error. If a null is proven as an alternate, a genuine null is proven as an alternate. Let's see some scenario. When I'm doing some audit as an auditor, the null hypothesis always says good thing. We already know by now data is normal, data is random, no differences, everything is equal, the dice is good, everything good. Null always says good stuff. So here when you're doing an audit, the null hypothesis, all the items are good. Alternate says no, the items you're auditing are bad. So null, alternate, and understanding should be clear here. When would I say I have made a type 1 error? When the items we were auditing, they were genuinely good. So that means they were null. But because of insufficient sample, or because of wrong sampling method, or because of a human error, you end up labeling this item as defective. Items were good, items were great, but because of insufficient sample, wrong sampling method, or human error, we end up labeling the items as defective items. A null, a genuine null, proven as an alternate. In a court of law, we know by default is innocent and alternate is guilty. Genuinely innocent person, because of false evidence, paid evidences, this guy is proven guilty in the court. Court has put this person behind bars because it's been proven in the court that this guy has committed a crime where genuinely this guy is innocent. Because of false and paid evidences, now this guy has been convicted there. Now, was this guy genuinely innocent? Yes. Did we prove the person guilty in the court? Yes. So a mistake has been made by the court. That's why we say innocent, punished situation. Null, proven alternate. Again, that you're making a mistake here. Well, somebody who goes for some sort of blood test or whatever, diabetes or pregnancy test or whatever, any test, and null says no diabetes, no COVID, nothing like that. Alternate says no, there is diabetes, there is COVID and all that stuff. Genuinely, the person is not diabetic. The person doesn't have COVID infection. But now this guy has a report in his or her hand which says that you're diabetic or you're COVID positive. Well, genuinely, the person was not diabetic, but you end up proving there is. So in all these errors, issues, you can see null is getting proven as alternate. Null is getting proven as alternate. Null is getting proven as an alternate. So typical way of like to understand whether it's a type 1 error or not, just try to understand. If there is no problem, genuinely there is no problem, but you end up proving that there is a problem, you're making a type 1. If there is no problem, but you say there is a problem, you call it type 1 error. Like here, items were good, but you say no, it's bad. The guy was innocent. We say no, this guy is guilty. The person was non-diabetic, but no, say diabetic. So when there was no problem, but you end up proving there is a problem, you're making a type 1 error. Type 2 is just opposite of it. Type 2 error is when you talk about type 2 error, beta error, or a guilty release situation, or a false negative. Here, an item which is genuinely defective, alternate, is passed as quality tested. This item should have been rejected, but now it has a label on it, QC tested. Why? Sampling errors, insufficient sample size, human error. Now you have passed a defective item, which will be released, obviously sent to the market. So it's alternate as proven as null. Well, a criminal is released due to lack of evidence. Everyone knows in the court. The judge knows that this guy is the criminal. We don't have an evidence to prove it. So a genuine criminal released out because obviously you don't have an evidence here. So alternate, genuinely the person is alternate, which is guilty, but you don't have a evidence to prove that is released. So that will be again alternate proven null. Well, you don't prove it, by the way. You don't prove null. And the person who's genuinely diabetic gets a report saying that you're non-diabetic. Well, this was the biggest scare during the pandemic period. Why? Because different countries had this testing kits. Because so this COVID testing kits were performed by different people. Well, their skill set, their training, how they do it. Well, the way they were collecting samples, that was different. So different people at different level and different countries had different quality of testing kit. Now, somebody who actually had COVID or probably was infected with the COVID, which is a mutant variant, and the testing kit was still going to test on the old version, so that if somebody got infected with the latest version of this mutation, the kit said no, there's no COVID. Why? Because the kit was not capable to detect the latest variants and all. You were not even testing for them. So yes, the kit will say, somebody gets tested, you're COVID negative. Yes, you're COVID negative, but on the old variant, not on the new variant. You never check the new variant. new variant was supposed to be checked, which you haven't checked because your knowledge, your training or your skill set or your capability is not there. So a genuine, like this is what happened. People had certificate in their hand, you're COVID negative. Well, these guys were infected with COVID. They was moving on, they were spreading it. Why? Because you have a license to roam around. You're COVID negative. So people traveled this country, that country with that certificate. And yes, they were COVID negative, though COVID positive, but with a variant symptom, not with the original one. But again, you have a certificate which is good enough that you have passed this COVID test. Well, that was a big scare. COVID negative one, like, so that was false negative situation. So genuinely there is, here we say there is a problem, but you say no. So when there is a problem, you prove no, there is none. You're doing a type 2 error. So you could get questions like scenario. The way I'm looking, you could get a question like the scenario-based question that you could be given a question like this, or question like this, or question like this. You will be asked to say whether it's a type 1 error or type 2 error kind of questions. You will be getting it. Now, quick check on this one, if it's okay and clear. If it's fine with everyone, type 1, type 2. Now, pretty much given the schedule, well, we will be working out these. So we're done with for the day, basically in terms of the content we have to cover, because that's the day 11 content. These are few tests we will be doing, like pre and post and the target validation test. And this is day 11, and then we do the control charts. And this is the day 12 part. Now, given that whatever time we have left, we are planned to do the remaining practice test. And yes, if you have some questions, if you need anything to be discussed till date, like what we have covered, well, we can discuss it first, and then we can take the practice test then. So if you have any questions to cover till now, whatever topic we have covered till now, anything that you want, probably going back till day 1, whatever you want, we still have some time. We can discuss. If you have any question, any topic which needs more clarity to be discussed, we can discuss it now, and we can take it up from there. And then pretty much we'll pick up the practice tests, which are the remaining measure, analyze, improve, and control, so that you can go ahead and give your green belt exam. That's what we'll be covering up. Need clarity on yield percentage calculation, how it's done? Yeah, absolutely, Giri. Just give me one quick second. We're talking about this yield percentage, which is calculated. This one you're talking about. This is the one we're talking about, yield percentage. Or you talk about throughput yield or roll throughput yield. The two different versions. One is based on LSL, USL. One, or the here also we have yield.
I'm asking about the LSL and USL.
This one, right? Okay, no problem. Let's pick it up. Yes, we can quickly go through the control phase also. Let's quickly pick up this question here, which is the LSL, USL based like calculation for defects. Like, let's kind of try this out, and then we can quickly look at the control phase, and we'll be which is solving the questions of till control phase now, for as far as green belt is concerned. So let's pick up some random numbers to solve the questions here. Let's try to create one, calculate, like let's pick up one question here. Let's do it right here. Let's create a scenario, some random numbers, and then we use the we will try to go and calculate it from different ways. First scenario, so question 1, like the question we're trying to, and these are all yield related questions, yield related in different scenarios. So A, I have been given only LSL, and only LSL scenario is given, and here let's say we have got let's say LSL mean standard deviation is given, and you have to calculate yield percentage. That's what we have here. And then we have this is question number 1. Let's say question 1. Let's create, then we have question 2, where we have both, like, no, only USL is given, mean is given, and standard deviation is given. Let's create question number 3, which is the third type of question I can see here, where both are given, LSL, USL, mean, and standard deviation. That can be 3 different scenarios we can look at. Let's try to solve this. Let's plug in some numbers and try to solve these questions. LSL, let's call it LSL of, let's say, keep it to like 10. minimum, it can't go less. If it anything less than 10 will be defect. The process average is say 16. And my standard deviation, let's call for now, the standard deviation is say 2.75, something like that. 2.75 is my standard deviation. And now let's pick up the USL scenario. Here, USL is the upper limit. Let's say we have a USL of 18, maximum limit. My process average is say somewhere like 17. And my standard deviation is say 0.88, some random number. Let's pick it up. And now we have both sides. Let's keep it this way. We have got 14 as LSL, 18 as USL. Average of the process is say 15.5, and standard deviation of the process is say 0.75. Let's just plug in any number. Who cares about it? And by the way, all these questions can be simply, you can plug in these answer questions, and we'll do that. Let's do one thing. Let's solve it properly with a proper manual calculation. And after that, we'll use the calculator to get the same answers. Let's get the clarity here first. So here, it is only LSL scenario. So when I have only LSL scenario, and I have to calculate lower side defect. So the probability of a process creating defect on the lower side. So only LSL scenario here, because here, so I'll find lower side defect. Probability of my process making a lower side defect. So my formula is norm dist for normal distribution. I'll put the LSL value, lower side limit X is 10, process mean is 16, and your standard deviation is given as 2.75, and I need total defect probability less than 10. This is what pretty much we're talking about. That is out of 1, and we multiply this with 100 to get defect percentage. So this process is out of 1, this is out of 100. Let's try to at least sketch and get this clarity what we're referring to here, so that conceptually we should be clear about it. What it tells me that my process mean is 16. It is right here, and it has 2.75 as standard deviation. So, well, that is 16 plus 2.75 will be here, plus 2.75 will be here, plus 2.75 will be here, minus 2.75 will be here, minus 2.75, minus 2.75. So that is how I have my normal distribution. And here it says my LSL is 10. So somewhere LSL is 10. So I guess let's kind of, if anyone can do this maths quickly for me on the lower side, because that's where we need to 16 minus 2.75. Can you give me the value just to make sure we get understanding here? Upper side, I don't care because it's lower side. 13.25. Thank you. Minus 2.75 one more time. 10 point. Okay, what is that? We have three values now. 13.25 minus 2.75. 13.25 minus 2.75.
10.5.
Is it 10.75?
No, 10.5.
10.5. Okay, minus 2.75 here.
7.75.
7.75. So I don't care on the upper side. Why? Because it's LSL scenario. Where is the target? Target is saying 10. So 10.5 is here. LSL could be here, somewhere 10. 10 is here. So all I need to know is what is the probability that my process will create a lower side defect less than 10. That's what it is. My mean is here. My LSL is here. So the probability that my process will create an item less than 10. So all I have to know is, well, I have to find the lower side defect. I can use the lower side formula, which is norm dist. I will use the plug like average. I will use LSL average and the standard deviation value. And I get to know 1.45% of my process will be defective on the lower side. While we're doing this, we can continue to do this on Minitab also parallel. Let's kind of keep plugging in the values in the Minitab and keep trying them out. Probability distribution, view the probability. I want to see my mean is how much. We want the mean of 10, like 16, mean of 16, 2.75 as standard deviation. I want to find lower side defect, less LSL, lower side defect less than 10. We saw this value, I guess, here it was 0.01456, 0.01456. That's a lower side. Convert into percentage is 1.45615. That's a defect percentage on the lower side. Now, if we have upper side defect, because it's only USL, upper side defect, well, I will be using the formula, which is again the out of 1. It will always be calculated out of 1, and we have to do multiplication of out of 1. We have got, so we have an upper side formula is 1 minus norm dist More than what? More than 18 is the defect. Process mean is 17. And standardization is 0.88. And we need total defect, upper side. That's what you get. And multiply with 100, which you will get here as 12 point some odd percent, 12.79%. Since we are doing upper side, let me write down the formulas here. It is norm dist, LSL, mean, standardization, and true. This is upper side defect. We will use 1 minus norm dist, USL, mean, standardization, and true. So upper side defect, lower side defect. Now we have got a form question where we have both sides here. So let's form this one for also. Let's do this calculation for this side also. We have a different answer question here. It is mean as 17. Let's put mean as 17. And standardization is given as 0.88. And we want to find upper side defect, so which is right side of what? Right side of 18. This is 0.279. Our right side of 18. That's what you have, 0.1279. Now we have both sides here. So we'll use both the formulas. We'll use this formula for lower side defect percentage. We'll use this formula for upper side defect percentage. And we'll get the total defect percentage. Let's see, let's try this one. I'm going to use the same formula here. Norm dist for normal distribution. LSL is given here as 14. Mean is 18. Standard deviation, mean is 15.5.
15.5.
Standard deviation is 0.75. And we have to use true. This one is 1 minus norm dist. Upper side defect, like upper side USL is 18, comma, mean of 15.5, comma, standardization of 0.75, and we will use true for a total. Just multiply this with 100 to get defect percentage on the upper side. Lower side, this is defect percentage on the upper side. And this is your total defect percentage, which is this plus this is going to be 2.31% defect. And let's see. And if this is my defect, what's my quality? So 100 minus this 100 minus this will be my quality percentage, 97.68%. That's your defect percentage. This is your quality percentage. This is your lower side defect percentage, upper side defect percentage. And let's try to solve this here with both sides given here. My mean was 15.5 and standardization was 0.75. Yeah. And let's find out the area, like directly find the quality area between what was this, 14 and 18? Yes, 14 and 18, the quality area. That is, this is 0.9768. 0.9768, yeah, this is one, 97.68%. Now, quick check on this one. Is it okay? I guess we had Giri. Is it clear? The lower side effect, upper side. And yes, you can solve all these questions right here in the examination. Look at this control limit. If you're both LSL, USL, let's try to put the values, whatever we did there. We had LSL of 14, USL of 18, average of 15.5, and standardization was 0.75. Look at this. Lower side defect percentage, upper side defect percentage, total defect percentage, total quality, and the sigma levels also. With everything related to that has been calculated. The second, where we had the only LSL scenario, we had only LSL scenario. What was the numbers? I don't recall that. Only LSL scenario we had 10, 16, 2.75. Let's say 10, 16, 2.75. 10, 16, LSL 10, 16, and 2.75. Only LSL scenario, that was the defect percentage, 1.45%. When you have only and this gives you the sigma level also. When you have only USL scenario, you use this calculator. So the USL question we had, let's go and check this out. USL question we had 18, 17, 0.88. 18, 17, 0.88. Here we got 18, 17, and 0.88. That's done. This is your sigma level. 12.79 was your defect percentage. So pretty much you can solve the questions here, there, wherever you want. Bottom line, you should know basically if this formulas can be used anywhere. So I hope it's okay with everyone. Like if you need any clarity, we can sketch them. Practically, yes. So when you start working on the project part of it, and that's why I want you to work on the project, because then conceptually your fundamentals will be clear. When you start dealing with it and start solving it, Minitab can do all that, or for that matter, even Sigma Excel will do this job for you. It's just about understanding the concept well. For examination, just get over with the examination. Because that's when everything what you're learning can be put into practice. You'll have a data, you'll have a problem. So then when you struggle with that problem, when you try to solve a problem, the concepts, what you were talking about is still theory, will translate into reality. It will be easier to understand. Yeah. Now, there was about control charts part. So from a green belt perspective only the green belt part. When we're dealing with the green belt, we will be required to know the control limits, the type of control charts we will be working on. So when I'm dealing with control charts, I got to keep in mind continuous data charts. When my subgroup size is 1, I will make an MR chart. When my subgroup size is between 2 to 8, I will make an X bar R chart. And when it's more than 8, I make an X bar S chart, and nothing more from an overview perspective. From discrete like attribute charts perspective, we will be required to know when to use which chart. And yes, if you are working on a defect charts, you got 2 choices. Either C or U will be depend on whether your sample size is a fixed sample or a variable sample. If it's fixed, you do a C. If it's a variable, you'll use a U chart. Same goes for defect. If you're trying to control and monitor the defectives in the process, you have 2 choices, either NP or P, which again depends on whether your sample size for audit is fixed or variable sample. So it will be taken care of from there on. Things to keep in mind from green belt perspective only, because like from black belt perspective, we only do things, the rules which will be discussed and the calculation of control limits, because then you will be making control chart, we'll be seeing every control chart, we'll be calculating the control limit and then matching the control limit, which we calculate with Minitab. So we will be able to understand how it's getting done. So we'll do all the control charts, calculate all the control limits and match our control limit calculated with Minitab. So we'll be able to understand how Minitab is calculating all those things. And so that's part of the black belt. You would not be asked any question on the rules and the control limit calculation in green belt. Well, you got to be definitely keep clear in mind that control charts are supposed to have control limits and not the customer specification limit. Specification limits are not supposed to be part of control chart. Control charts have control limits and these are calculated and nothing to do with the customer. These are calculated based on a formula. Every control chart has its own formula. So they will change. If your data changes, the limits will get recalculated because it's a formula. If the values change, the answer will change all the time. Control charts and normal distribution are the same thing. We all know one is a vertical one is a like horizontal one. If I look at a control chart, what can I understand? I can simply understand whether the control chart is in statistical control. If I don't see the red dots, the special cause variation, the process is in statistical control. Well, if there are special cause variations in, I can see that the red dots will be visible, but I cannot tell you whether the process is in control, whether the process is meeting the target or not, because I can only see control limits, not the specification limits, which we definitely add manually, but not a part of control chart. We do it manual addition, correction to that. But by default, a process which is in statistical control does not mean it's meeting target because we don't know what's the target. So, well, for example, my process, like people have appeared for some examination and these are examination score and we make a control chart for the examination score. It tells me my examination average is like 50 average. And these are the scores of different past students who have appeared in this exam. It tells me the maximum based on the data. It has calculated UCL. It tells 80. LCL, it says 20 with a mean of 50. What does it tell me any red dots? No. Is it good? I don't know. It tells me my average score is 50 and it can go maximum up to 80. It can go lowest up to 20. But I don't know. What's the target? Well, do you have target? No. Well, if I put the target line, if I say my passing marks is 90, even though you don't see special cause variation, the entire process is bad. Why? Because it's all failed. Is it showing any variations? No. Any special cause? No. So process which looks stable, the process which looks under statistical control with no red dots, no special cause, may be defective completely. It's okay. It is controlled, but not good. It is controlled. It doesn't show unexpected variations. It is controlled, stable, and yes, it can be improved easily because it's stable. But is it good? No. Like in this case, everyone failed. This is stable data, but failed. That's it. So I can't look at a control chart and say whether it's meeting the target. When the process is stable, controlled, statistically controlled does not mean it's meeting target because I don't know the target here. When I see a red dot, the special cause variation, they are not a confirmation of a defect. Special cause are indicators. Special cause tell you that there is a change happening in your process. Please investigate. The change could be a good one. Do a root cause analysis and find out, is it good for you or not? And if it's good for you, why? And go and repeat more of it because it's good for you. A red dot, which may be bad for you, investigate why and fix it before it becomes a problem. So a red dot simply tells you that change has happened. A change can be good or bad change. I don't know. It depends on what are you auditing. If your cost is going up, it's bad. If your sales is going up, it's good. So it doesn't mean like red dots, whenever it'll come, it'll be always good or bad. Well, it can be good, it can be bad, depending on what are you auditing. All in all, that's all we have to keep in mind from a control perspective. There's nothing much in here because it's just a basic overview. Is it okay? I guess that was Simon's question. Yeah. Perfect. Let's then go ahead and pick up this discrete and quantitative data. Yes, absolutely. Yes, like qualitative and quantitative, right? Let's go and quickly talk about this. First thing first, continuous data. Continuous data. First, this is continuous data is always numeric. Always numeric. Why? Because you will be measuring it using some standard unit of measurement. Some standard unit of measurement will always be there. Like weight, like kilogram, minute, like in time, minutes, seconds, like pound, kilo, degree Celsius, whatever. These units will be there. So Celsius, Kelvin, all these are units. But whatever unit is applicable. So what you will be using with the global unit of measurements. You can always write a continuous data into infinite decimal places, infinite. So you can always write down, say my weight is, say 78 point something. I can say, okay, that's my weight. Yes, I can do that. It can go till infinite decimal places. If you have a scale, it will go on and on. Depends you have a scale or not. But again, it has the limit, infinite limits here. That is with the continuous data. Discrete data, which is with discrete data, can be both qualitative and quantitative. Quantitative discrete is count, percentage. First of all, count, there is no unit of measurement. Percentage is no unit of measurement. So first of all, it's not a continuous data. It's not a continuous data. In case of dealing with the count or percentage, it is not a continuous. Why? Because there's no unit of measurement. This cannot be in like a decimal places ever. You cannot have this written in decimal places ever. Why? Because count cannot be in decimal. You will have you will always have whole number, like count of people, count of machine, count of cars. Bottom line, basically you will be always having a whole number, always a whole number. In case of percentage, yes, this can get into decimal places, like quality percentage. Can I write this quality percentage written like this? Say my quality is so and so. I can do that, but it's still a count. It's still a count. Why? Because percentage means percent. Per means out of 100. So we're counting out of 100. So in case of percentage, if I do get this A, first of all, percentage is not a unit. It is just a proportion. So if I make, like if I had, for example, we made these many errors out of, say, these many items. Well, we want to find defect percentage. What do I do? What is the meaning of defect percentage? It means if you make 2541 errors out of 6852, then how many basic element, how many, which is X, defects out of 100? That's what you do. So you will be doing this as defect percentage. You will calculate your defect percentage here by doing this maths here, which is technically you will be doing 25 6501 multiplied by 100, and this all divided by this value of 6582. All divided by, I forgot the sign, 6582. That's what you do. And let's see if I want to go and do this maths, this is what I will end up doing here. So let's kind of solve this one. If it's 2541 divided by multiplied by 100 divided by 6582, that's 38.605. That converted in decimal. But how? Aren't you counting? This is what you're doing, is these many errors out of this, then how many? You're counting. So it's underlying data. It's underlying data. It's still a count. Percentage are made from count. Then, so this is quantitative discrete data. Quantitative. In qualitative discrete data, you have got three types. Qualitative discrete will have three types. We have got binary, we've got ordinal, we've got nominal data. The binary, we have got like yes, no, true, false, pass, fail. Yes, no, true, false, pass, fail kind of data. We have only two things. Even 1, 0 is a binary number. Ordinal data, whenever we talk about ordinal data, it's like ranking data, ranking, rating data, like excellent, good, average, bad, that kind of data, or for that matter, rating scale of 1, 2, 3, 4, 5. That is an ordinal data. Normally, it is like anything, like I say, red, blue, green, yellow, or for that matter, the name of department, like say, for example, HR department, quality department, or production department, IT department. That's just a name. Doesn't tell me which is bigger, which is smaller. That's always, this is what we call qualitative data, which is discrete data, is also called attribute data or categorical data. These are discrete quantitative. This is technically discrete quantitative. This is discrete qualitative, and this is discrete quantitative. Now, quick check, Mr. Imran, if it's okay and clear. Okay. Clarification on ANOVA. Well, why not? Let's go and quickly check this. ANOVA. One-way ANOVA testing. Very sensitive. Well, practically applicable for comparing means of multiple groups. Means. But condition number one. Well, first of all, output data, whatever the output Y, has to be random. So how do you check that? Run chart. Null says data is random. Alternate says no, data is non-random. Data is non-random. So when you perform the run chart, you will get to know whether data is random or not. So if data is random, continue testing. It's not, it's eligible. But if it's non-random, you have to perform Kruskal-Wallis or Mode's median test. You can't use mean test anymore. If it's randomness issue, you can't use average testing. Now, condition number one, qualified data is random. Now you have to compare variances. Variances must be equal also. So how you perform here, the test was called test for equal variance, which will give you result from Bartlett method. Bartlett. P is missing, Bartlett. The null hypothesis says variance is equal between groups. Alternate says no, it is different, it's unequal. So two things can happen, either variance is equal or unequal. If variance is equal, continue testing. If unequal, use Kruskal-Wallis or Mode's median. Remember, last one is when we'll go with ANOVA. Well, now since data is random, how do you know? Through run chart. Variance is equal. How do you know? From Bartlett method. Now you can compare means. Null says means are equal. Alternate says it's unequal. And the test name is one-way ANOVA. That's you do. These are the steps you got to keep in. Well, Jahan, is it okay? The three can basically have to go to the portion of ANOVA after you've filtered all these elements. Anyone has any other question that you probably need more clarity on? So let's do one thing. Let's, if it's okay, we can take a quick 10 minutes break, and then we can come back and sort of take up these questions, the practice test we have left with. Let's do that. Let's take a quick 10 minutes break, and we will resume, and we'll just finish up the portion of green belt so that you can give the green belt exam anytime in the coming week. To be a continuous data sample size question, because in discrete you will not see a standard deviation. Let's see. Let's go to the Excel sheet where we have calculator page. We go on the top, we go and plug in the values here, and we'll see Z is confidence level. It says Z is 1 point, this is 95% confidence is 1.96. 1.96 fixed value, which is Z value. Sigma is standard deviation 0.018. I put in 0.018. And margin of error is given as 0.003, 0.003, and it's 138.29 will be rounded off to 139 sample, and that will be 139. Thank you, yes, Simon, that's correct. 139 samples. Augusta is planning to conduct a survey for product launch and decides to pick up every sixth person coming out of a shopping mall. Which sampling method is Augusta using? Thank you, that's a systematic sampling, perfect. How about this one? Which kind of question is it? Continuous data or discrete data? It is absolutely yes. It is discrete. You do not have a standard deviation given. The unit of measurement is not this percentage, which is given here. Let's go back to the percentage one side here. So this is discrete sample size calculation formula. Well, let's first of all see what all information. 95% confidence level. We'll put Z value as 1.96. Then it says margin of error is 2%. So plus minus 2% is the margin of error. Let's kind of put in plus minus 2% is 0.02%. And probability of success, it says Nora has no prior information about process quality. What should we use here? If we do not have historical probability known, what should we use as probability of success? We don't have prior information about the probability of success. What should be used in case you have no idea about probability of success? Absolutely, Sejo. 50%, yes. You don't have an idea, go with 50%. You need 2,401 samples, which is right here. It's a market research agency. They're trying to do some exit poll result after elections. For that, they have estimated the sample size will be 2,500, and for which they have to find the right way of collecting the samples. From large population, you want to predict about the success rate, which party will be winning this election. Which method will be best suited for that? It has to be a stratified one. Because people in this is a mixed population. This is a mixed population. People will be from different age group, different religion, different areas, income class, gender. So I have to stratify this population because every group will behave differently. It's a massive population. Whenever you talk about mixed population, you always go with a stratified random sampling. First, collect data, stratify this, find the groups in the population, and then find from every group, pick up some data randomly because they are same or similar. This question is about continuous or discrete? Discrete, perfect, yes. So we are given 95% confidence level. This is 95, 1.96. It tells you 94% as historical quality. I know this one this time. So I can use 0.94 here, 94%. It says margin of error is 2.5%. So we'll use 0.025, 2.5%. That's 347 samples. All I have to select is 347. Measurement of same part using same equipment by the same person, it is called A, perfect. Repeatability, perfect. There is a problem in this setup of data collection. Or what is the problem here? Saima says, okay, yeah, you're right about that. D, it's not balanced. Look at this. A has been audited 3 times. B has been audited only 2 times. C has been 2 times. If you look at operator 1, operator 1, 2, operator 1, 3, operator 1, 4. 4 times operator 1, but 1, 2, and 3 times operator 2. It can't be done this way. You need to have each person audit each item equal number of times. It is not right. Reproducibility refers to variation because of. Thank you. You're correct about that, operator. Operator variation is reproducibility. A minimum dash trials are required for repeatability and a minimum dash people are required for reproducibility. Absolutely, the last one. Minimum 2 will do the job, but we don't recommend. We always go for 3 at least. But worst case, yes, 2 will do the job. Kappa statistics for rejection is perfect. Yes, it's less than 0.75. It will reject the measurement system. Let's see which is the correct answer. You have ANOVA test results, 3% for repeatability, 12% for reproducibility. Total system error is 15%. What problem do I have in the measurement system? Absolutely correct. It's the operator. Repeatability is equipment, which is great because rule says less than 10% is excellent. So equipment is excellent, definitely excellent, 3%. Well, amazing. My problem is with the operator. This guy is outside 10, and that's why my overall error also looks high. So I have to control my operators, which is high. So that's why operator variation is the culprit. Pretty good one. Let's go and check this one now. Which of the 7 quality control tools will be used for establishing statistical relation between hours and the attrition count? Gary says D. Okay. Which one, in your opinion, is the correct answer? We got one answer here. You're correct about that. Absolutely. Scatter plot. Both are numbers. Perfect. Cabs generally arrive late to the office and resulting in loss of work, basically. Operation manager collects office reporting time for the cabs and finds that p-value for normality is 0.021. What should be chosen for central tendency? Absolutely correct. Data is non-normal. You have to choose median. Perfect. Yes. Thank you. Which test will be used for testing stability of the data? Statistical test. Perfect. Yes. Absolutely. Yes. It's run chart. See, honestly, there can be confusion with this, and please, that's why control chart is also going to tell you the stability. Run chart will also tell you stability, but this is test, which will give you p-value. Control chart will not give you p-value. Run chart is a test we perform, which is why we're talking about p-values part. Survey was conducted among patients of 2 major hospitals to see if there is a difference in average ratings given to different hospitals. Which test will be used to compare them? Absolutely. No, we've got 1 correct, 2 correct, 3 correct, I guess now. Well, yes, that's 2 sample T comparing the averages of 2 groups. We got 2 major hospitals getting compared for their average ratings, average comparison for 2 groups. It's going to be 2 sample T. Annex Corporation purchases raw material from 3 different vendors. However, there are complaints about variability in the quality of raw material. Which test will be used for this one? And yes, the variability test for look at the question. It's talking about variability in the quality of raw material. We are trying to compare the variability, not averages. So it's for comparing the variations of multiple groups. I will perform test for equal variance, I will get result from Bartlett method. Bartlett method for comparing for 2 groups is F test. More than 2 groups it's Bartlett. Please watch out for the words variability, not the average. This is a tricky one. This one is tricky one. You don't get that kind of question, but purposefully inserted here. Just have a look at it. Test results from 2 variance tests or test for equal variance will give you result from which one? Yes, you're correct about that. Absolutely correct. F test. And let's see, slightly tricky, slightly purposefully given that way. Say if I have to compare a variance of 2 groups, two variance tests will give me F test. That's the only thing which will give me. Because two variance can only be used for two groups. It will give me F test. Test for equal variance can be used for two groups also. When I'm comparing two groups, it will give me result from F test. But if I'm comparing this for multiple groups, same test for equal variance will give me Bartlett. Now, since for these both the tests, the common test is F test, the answer is going to be F test. Because two variants cannot be used for multiple groups. So the common test is an F test, so you will select it. Or you don't get that kind of answer, but bottom line should be prepared from interview perspective, yes. Is this data random? Looking at p-values, is this data random? Yes, absolutely correct. Yes, absolutely perfect. All p-values are more than 0.05. Since all p-values are higher than 0.05, data is random. No patterns are present. Sam uses 99% confidence level. What is the level of significance here? Absolutely correct. 1%. Remaining 1%. Absolutely yes. This one is a tricky one. Let's see which one, if you're able to figure this out. There are 4 different projects are compared for the effort. So project A, efforts like hours spent in project A, hours spent in project B, hours spent in project C and D. So 4 projects, their hours spent are compared. When you compare the hours efforts, basically hours data, you found that oscillation p-value is 0.004. How will you compare if these projects are statistically different or not?
Correlation.
Oh, that is perfect. Yes. Thank you. Well, I would have compared averages. Well, 4 groups, we would have compared averages, which is, answer would have been a one-way ANOVA answer would have been. But purposefully, there's a p-value given here. For oscillation, data is non-random. If the data is non-random, can't use ANOVA. It has to be Kruskal-Wallis. Ideally, if this p-value has been purposefully given to tell you that this data is a non-random data, since the oscillation p-value is less than 0.05, you cannot use ANOVA in that case. You have to do a Kruskal-Wallis or Morse median. So thank you. That's correct. R value is given as minus 0.68. What's your interpretation here? Perfect. Yes, that's a moderate negative relationship. Perfect. Yes. You're comparing average life duration of 4 different types of bulb. Which test will you use here? Perfect. Yes, absolutely. We talk about averages and you correct about 4 different groups, more than 2 groups. Average comparison. It's got to be ANOVA. Showroom owner wants to check if better lighting conditions measured in lumen. Brightness of light is a continuous data. It is measured in lumens, brightness. Will it result in higher sales? Which statistical test needs to be done to check if this is actually true? One correct answer. This is brightness of light, and we're talking about sales. It's measured in lumens, and the sales. It is going to be a regression test. We're talking about brightness of light in one column. Like, so probably, I don't know what's how you measure that. It could be like 50-watt bulb, 100-watt bulbs, 150-watt bulbs, or 200-watt bulbs. And my daily sales converge, like what was sales. So I'm talking about in relationship between the brightness of light and the sales. Well, is there a statistical relationship between 2 variables? We want to find a relationship here. So, well, if you want to find a relationship between 2 numeric data sets, it has to be regression. Regression or correlation for that matter. I will do a scatter plot as a graph for this. Which one is the correct answer? Slope first and then intercept. Please keep this in mind. The order has to be slope first and intercept. What's your correct answer here? And that is absolutely correct. Slope is 45 and intercept is 10,000. You're right about that, 45 and 10,000. Can you predict this question, this sales, whatever profit here? Absolutely correct, Simon. Absolutely. Yes, that is the correct answer. It's 15,000 plus 125 multiplied by the advertisement cost, which is 500. So multiplied by 500. This is minus 65 multiplied by the overtime hours of 125. You do this maths. So 15,000 plus 125 multiplied by 500 minus 65 multiplied by 125 is going to be 69,375. The second option is the correct one. Just have to substitute the values of these excess. This. And that's the end of this. Why? Because let's see, that's a black belt question. And this is all black belt from here on. Just leave it there. Leave them. We'll pick them up next week when you complete the black belt preparation. Now, Wilma implemented strategies decided by the Lean Six Sigma project team and wants to check if process has statistically improved and achieved the desired target. Which test will she be using to validate if the target has been achieved? The target has been achieved. How will we check? Target validation test is what you're talking about here. Which test will you use to check if your target has been achieved? If your target, whatever target was set. No, that's not. That's for pre and post analysis. That's pre and post. One sample T, week by week, week by week, week by week, we check one sample T. Did I achieve my target? One sample T. When you're able to verify for one sample T, then you do a paired T to do a before and after. Before and after is paired T. Which of the tool is called RCA tool? Which of these is the RCA tool? Yes, that's correct. 5Y. Well, Alembic Pharma has come up with a new drug and claims that it'll reduce the blood sugar level significantly. Regulators want Alembic Pharma to present statistical results showing the new drug is effective in reducing blood sugar level. Which test they have to perform in the given situation? That is going to be paired T test. Before giving the medicine, what's the blood sugar level? And after giving the medicine, what's the blood sugar level? Pre and post analysis of the same people. So you get, say, 15, 20 people who have got a blood sugar problem, measure the blood sugar level, and then give a medicine, again measure the blood sugar level. And paired T test is for same people before and after. Paired T test. All medicine companies, all pharmaceutical industries have to do a paired T always. Always. The indicator for prioritizing risk is called. Absolutely correct. Yes. That's anyone else has any option here? Absolutely. Risk priority number, RPN number. Risk priority number from FMEA. Well, we're doing an FMEA. We found this like a 3 risk. Which one will be prioritized first? The Simon says 1. Okay. And you're correct about that. See, if you look at RPN will be same for all the 3. So when my RPN is same, then we go with highest severity. Absolutely yes. Which is the first one. Because RPN will be same in all the cases. POCA, yoke is also referred as. Absolutely correct. Mistake proofing, error proofing, all the same. All documents are closed by the end of the project except. Absolutely, that is going to be the correct one. FMEA. Risk never dies. Risk never dies. FMEA. And from here on, it's all black belt questions. This is black belt. This is black belt, black belt, black belt, black belt, black belt. Yeah, that's all black belt. So coming to the last section. Control limits for the process is defined by the customer. True or false? Control limits for the process is defined by the customer.
False.
It is false. Control limits have nothing to do with customer. Specification limits are given by the customer. Control limits are calculated. They are given, not given, they're calculated based on a formula. Every control chart has its own formula. They have nothing to do with the customer. Presence of special cause in the process indicate there is a problem. Visha says B, and you're right about that. And I'm like it's yes. It's not necessary. See, red dots are just telling you there is a change happening. The change can be good, the change can be bad. Decide it based on what you're auditing. If the data is going up, it's sales process, production process, good for me. Let it cross. I don't mind. Upper limit, higher the better. So it doesn't mean it's always a problem. If my cost is going down, it's going below the lower control, good for me, lesser the better. So it does not mean it's a problem. It's a change which is happening. Well, you can decide whether change is good for you or bad for you, but special causes are not a defect. They're confirmation of a change in the process, not a defect. It may be, I don't know, but what it simply tells you, there's an indicator, which is a special cause variation telling you that the change is happening in the process. Alan wants to check if machine is performing under statistical control. He picks up one sample every 3 hours. Which control chart will he be using? And the answer is wrong. One sample every 3 hours. It has to be a single sample with IMR, individual. One subgroup is IMR, individual samples are taken. This one sort of little tricky. Please try to see which answer would you be using here. A software developer wants to observe the number of bugs, which is defects. Bugs are defects. Now, for various programs created, which control chart will be used here? It said bugs means defect means it has to be discrete charts. We have got 4 C, U, P, and NP chart. These are meant for like defects.
I think NP.
No, that's what we need to understand. Fixed samples and variable samples. So you're talking about, first of all, bugs are defects. So these are bugs which are defects. And so that means it has to be either C or a U chart. Now, big question is, you're looking at multiple various programs created by the team. Now, will every program have equal number of like code written? No. There will be variable codes written because some programs will have like longer codes, smaller codes. So variable sample will be there when you're auditing it because every program will not have exactly the same code. So variable sample, and this will be a U chart in that case. In this case, it will be a U chart. Next one, let's see here. An auditor decides to audit 20% of daily output to check if defective items produced are in statistical control or not. And you are right about that. Defective items. When you say defective items, I have got 2 choices, NP or P. Now, which one are you talking about? Giri says P. It is NP or P. Has to be a P chart. 20% of daily output is a variable sample. 20% of daily output will change. Why it's not a fixed sample? Because my daily output will not remain same every day. So 20% will not remain same every day. 20% of whatever is getting produced is going to be picked up. So it's a variable sample. That's the catch we talked about. It's not a fixed sample. It's a variable sample. So it's a variable sample for defective. It's going to be P chart. As data changes, control limit changes. Yeah, absolutely. Why not? They will get calculated. Again, yes, you're right. Process under statistical control always meets the customer expectation. False. Absolutely. Why? I don't know. Because I don't know the control limits. It may be in control, but how can I tell you whether it's meeting expectation or not without knowing the limits? Customer targets are not there. So it's a false thing. Rest are black belt questions. These are all black belt questions. Well, this is all control limit calculation. All are control limit calculation questions. So black belt will be, all these are control limit. So that is all pretty much on this one. So if you, whatever we have worked on, I would highly recommend, please go back and like say, please Excel, download this Excel sheet for your exam. So today, like allow me time till tomorrow morning. I need to kind of do some bit of cleaning activity in the Excel sheet. We'll like to a later part, I've sort of messed up with some of the data. So I'll just update the Excel sheet by tomorrow morning. And please do download the Excel sheet and do practice this once because you already have answered it. You put, which is pretty good. Like, so I'm not at all worried or I'm not at all even thinking about how will you do in your exam. It'll be fine. Don't worry about because like practically looking at your responses, it gives that immense confidence and like sense of satisfaction. No, that will be done. So, but do at least pick up this once and do it yourself. The questions that we did will be more than enough. Give your exam, you'll be fine. Well, we'll then meet next week and take it up from there. But again, allow me time till tomorrow morning to upload the file after doing some bit of cleaning up because I've written all, like messed up everything. Let me just reformat and kind of put all the data in a right structured way. I'll share it tomorrow morning. Is it okay with everyone? Perfect then. That will be all. And please do try out if in case you come across any question during the week, just don't wait. Well, just ping me on the WhatsApp. We'll be more than happy to kind of give you clarity. If you like solving something, you're facing a problem, let me know. I'll be more than happy to kind of like respond to your question and clarify it for you. And yes, please take good care of yourself, and we'll be connecting next week. Thank you, everyone. Good night. And I'll be uploading this file tomorrow morning.
Okay.
Thank you.